All right, welcome out there. This computer does not want to wake up very quickly whenever I need to use it. So, all right, so let's see. Let me get some notes going up here and we'll let the good times roll. All right. Okay, let's see. Okay, let's bring up both sections. Let's see. All right, this will warm up. Now, time to share the screen. Okay, let's see what we got here. Share screen. Can you hear me okay?
Yes, sir.
All right, thank you. Thank you. Beautiful. Just want to get a confirmation there. That's fine. Just never know. I'd hate to get off and start talking for a while and then realize there was no audio, so that'd be kind of embarrassing. All right, thank you for the confirmation there. I appreciate it. And let's see what we got going on here today. Here we go. Probability distribution for a discrete variable. We're going to talk about what discrete variables and versus continuous variables are. In chapter 6, when we learn about the normal distribution, that's going to be a continuous, but these two sections today are based on discrete. Now let's just talk about briefly what a random number variable is. Let me see what's going on over here. Okay. All right. Random variable. It's a variable that for a probability experiment where X has to be a numerical value associated with each outcome of the probability experiment. So X has to be something that's numerical. And there are two types of random variables, discrete and continuous. So let's take a look at these definitions, because I could certainly have one of these questions on exam 2, ask you if you think this is the discrete or continuous. I guess you'd have a 1 out of 2 chance of getting it right, but I think you'd like to feel comfortable enough where you got a 1 out of 1 chance of getting it right, so you don't have to flip a coin to get it right. So discrete means that it has a finite or countable number of possible outcomes. It only has a specific possible outcomes. Anything that says, it's not always this case, but anything that says the number of something pretty much guarantees you're talking discrete. It's going to be something, but it's not always just countable. I'll talk about that, but finite, we'll talk about what that means too, but it's only, we'll look at something here later, or if I don't have it in the notes, I got rid of some stuff out of the notes. I can add it back real quick, but it doesn't have to be just things that you can count, but if it is countable, for sure, it's discrete. Now, continuous means it's an uncountable, infinite number of possible outcomes, like represented on an interval and a number line. Now, back in algebra days, learning like interval notation or something like that. I'll just write something here, just scribble it down here real quick. If you were talking about real numbers, and you said, between 4 and 6, and I could have put the equal. Well, actually, I will. I think I'll put the equals at one end just for the heck of it. That means any theoretical real number fits in that interval. It could be exactly 4, but it can't be 6, but it could be 5.99999, forever, like that. It can be like that. It can be any, 4.78923, blah, blah, blah. I mean, you can't list them, in other words. For a continuous random variable, you can't list all the possibilities. I mean, they can be contained like they are here, contained between two numbers, but you cannot list every number in the interval because it's just impossible. Now, variables that are all continuous, measurement variables are generally continuous, like time, height, volume, temperature. Things that are kind of continuously moving. Time, can be measured in very minute detail if you have the right kind of device. Even like, height, whatever. So let's say, you're keeping track of, your child's height. And let's say in a year, they've gone from 42 to, I don't know, 45 inches in a year. Does that sound reasonable? I don't know. We'll assume, I don't know. Might be off, but anyway, whatever. You measure them at 42 and you measure them at 45. Now, during that growth from 42 to 45, they weren't just 42, 43, 44, and 45. They theoretically cover all possibilities in that interval. So if you had the right kind of, measuring device, basically, but, your child at some point would have been like 43.56, inches at some point or whatever like that. So it means that even though if you can't really measure it, theoretically, it would have been continuously moving between those two numbers. It wouldn't have been just only the whole numbers. So let's look at some of these examples. And I don't want to make this, too bad here, basically, but let's just kind of let's go through these examples. Determine if these following random variables are discrete or continuous. The number of goals scored in a soccer game. That would be discrete. Now we're saying even before, it means the idea is it would either be 0 or 1 or 2 or 3. It doesn't have to have a upper bound. You don't have to already know how many goals were scored. You just know it's going to be something like that: 0, 1, 2, 3. In other words, there's no chance. We have to list them all out because there's no chance you're going to have a 19.53 in there or something like that. So it's going to be a whole number. Same thing with the second one: number of home runs in a baseball game. Same thing. Time it takes to complete a baseball game, that's continuous. Now, I know time is, often just recorded in, hours and minutes and maybe seconds, but theoretically those seconds could be, more decimal places than we actually see or whatever. It's not just those specific whole numbers. It's like if you're watching a hand on a clock, it'll be continuously. Nobody probably looks at clocks anymore, though, do they? But like a second hand moving on a clock would be sort of continuously moving. I guess we're usually used to looking at digital. Number of defects on an automobile final inspection, that would be discrete because it would be a specific measure. The temperature of a pizza oven at a particular time, that's continuous. Temperature would be continuous. Or suppose you have an oven. My old oven used to do that, but my new one doesn't do it. I kind of miss that. Whenever it's warming up, it shows you what temperature it is. Now I just have to wait for the beep when it hits the temperature, but that's all right. But anyway, if it's just showing, it's going to show whole number temperatures, obviously. But as it's increasing, if it's going from, maybe it's just showing it every 5 or something like 300, 305, 310. It's not just those numbers only. It's moving through those numbers, continuously moving through, even though it just displays the whole numbers. In other words, hopefully that makes sense. I'm not trying to make this too confusing. Well, I probably am making it too confusing, but temperature, continuous. Now here's an example where it's discrete, but it's not countable. And we'll look at some more examples of this later too. Let's say you make a $5 even money bet in the casino game of roulette. If it's an even money bet, that means you're either going to win $5 or you're going to lose $5. That's discrete because it's only going to take on those two values. It can't take on anything else. Nothing between there, whatever. So, and we look at some monetary problems here later. You're going to see that anything involving monetary values that are discrete, you can have negatives. We're talking like profit and loss. The number can be negative, but if it's only specific values, that's what makes it discrete. The amount of liquid in a 16-ounce bottle, that's continuous. because it can be theoretically, when you pour something, let's say water, for example, you pour water in there, it can be anything between 0 and 16. And theoretically, you'd have to have the right kind of measuring device, but it doesn't have to be just whole numbers. You could pour some in there and it could be 12.57 ounces or whatever like that. So number of questions answered correctly in a multiple choice exam with 20 questions. That's discrete because it's only going to be, so the difference between this one and the home run and the soccer game, at least you know whether it's before or after the game, but this one, the answer is going to be, the X is going to be either 0, 1, 2, 3, 4. It stops at 20. You wouldn't be higher than 20. In a soccer and baseball game, you wouldn't know until what the highest number was going to be until, after the game was played or whatever. But anyway, all right, we're going to focus on discrete right now and then look at a particular continuous one later here. So a discrete probability distribution, what it does is, and these can be either written horizontally or vertically, that's not important, is all the X's, you list all the X's, then you list the probability that goes with that X. Each X will have a certain probability that it happens. Now, we're not going to get too rude with these, X's and how many of them. I don't think we look at the homework. I don't think it's too bad. Homework may have some that are more than what I would put on a test, but they shouldn't have too many of them. Like I don't want to have anything that goes 0 through 20, or something kind of rude like that. It's just too much effort. But yeah, so vertically, horizontally, but you have to, you line up the appropriate probability with whatever the X is. So let's start with a real easy one here. Rolling a single die. We've talked about this last week. Single 6-sided die, and let X be the number of dots facing up. So over here, I'm just kind of identifying as a sample space, basically, what are the possible X's. The X's are going to either be 1, 2, 3, 4, 5, 6. That's it. And here's the probability distribution for that. So there's 1, 2, 3, 4, 5, 6. And each of them has a 1 out of 6 chance of occurring. Now, one thing to make this perfectly clear, the probabilities aren't going to be always equal for every problem we do. That's not a rule or anything like that. It's just the result from this example. But they would, these would certainly all be the same probability. Now, here's a couple of important things for a valid discrete distribution. The first one we talked about a couple of weeks ago when we first were learning probability, that it's got to be the probabilities, the individual probabilities must be between 0 and 1, or percentages, that's 0% to 100%. But this one, the probability, the sum of the probabilities must add up to exactly 1. Because what that means is that you have a 100% chance that one of those outcomes is going to occur. That's basically what it means. In probability, we learned that or, means add. So, so 1 or 2 or 3 or 4 or 5 or 6, you'd add up all the probabilities and there's a 100% chance that you're going to get one of those outcomes. So that's good to know if you were actually trying to come up with a distribution and weren't sure what you were doing wrong. First thing you want to do is check and make sure it adds up to 1. That's important. So let's look at these examples and see if these distributions, are valid. When we say valid, means satisfies those conditions above. Valid doesn't, mean right, because like, for example, it doesn't mean, depends on, well, these don't actually have a story behind them, so it doesn't really matter. But I could sit here with this dice problem and I could rearrange those probabilities and make them add up to 1. So technically that would be what we call a valid distribution in the sense of satisfying these rules, but it would not be accurate. So the valid doesn't mean accurate if you know how to calculate them. These are just made up. There's no way you're just trying to test for if they satisfy these two rules. So now I put it at negative. Remember, X can be negative, X can be anything. It's just the probabilities we're looking at. So for the first one, each of those 4 probabilities are all good. They're all between 0 and 1, nothing weird there. But if you add them up, you get 1.1. They didn't add up to exactly 1. So that makes that distribution just basically not valid or impossible or however you want to call it. The next one, you look at the probabilities. They all look good. I did see on the calculator. Just add those 4 probabilities up, add up to exactly 1. We call that a valid distribution. The next one. Now, the next one, I didn't put this in the calculator over here, but I did this on purpose. I made them add up to exactly, if you check that, they add up to exactly 1. But before you would even do that, we got a negative probability there. So it's automatic game over. So once that happens, you don't have to add them up. But I did make them add up to 1 just for the heck of it. But a negative probability, game over, not a valid distribution. All right. Now, let's say we have a distribution, there's a missing number in it. Can we figure out what number we need the missing probability? Can we figure that out? And we can, because if we only have one missing number there, by the rule we just saw on the last page, they have to add up to exactly 1, correct? So what I did is I added up, I didn't show the result, but I just put them in parentheses here. But you add up those other 3, and you take 1 minus the sum of those 3, and that will give you the missing value. And then you can easily double check that. So 1 minus those 3 would give you 0.16, and then you could double check it real quick, and which I have before, and this isn't a new example, so I know it's right. But obviously if you want to check it, but it does add up to 1. So it's just 1 minus the sum of the other 3. So that's not too bad. Now here's one where they're giving you a distribution. I just sort of did this over to the side, but it's unless it's a mistake. But anytime they give you a distribution that you're answering questions on, whether it's homework or on a test, I shouldn't mess that up. You know, it's going to be a valid distribution. You can check it if you want to, but what would be the point of me asking a bunch of questions for you to figure out, if it wasn't valid to begin with? That's different than what we just did about verifying whether or not it's valid. I could obviously ask that too, but I just went ahead and just for our own edification, I verified that. Well, of course, I made these numbers up, so I kind of wanted to check it myself. But I'm assuming that anything in a homework problem is going to already be properly checked or whatever. But okay, this is good. I like to have this this is good on the second exam. These are one of my favorites. Got to pay attention to the inequality symbols there. Got to be careful. So as long as you're careful with the inequality symbols, should be okay here. But people will miss this on a test. They just have to be careful. Between 1 and 3, notice it has equals at both ends. So equal, that's going to include, it's going to include 1, it's going to include 3. So that means X is, because it has equals at both ends, 1, 2, 3. So the probability that X is between 1 and 3, that's also known as inclusive because it's including both ends. You would just add up the 3 probabilities, 1, 2, 3. So getting this final answer of 0.61, as long as you know the things to add up, it's easy. But you have to figure out the right things to add up. See, so in other words, yeah, if you get these 3 numbers right, and it's these 3, there's almost impossible you could mess this up. But you just have to know it's those 3. Now look at the next one. I've got the equal at 1, but then the not equal at 3. So that means I don't include 3. So it's just 1 with 2. So I just add up the first 2 and get 0.29. So see the difference in these 2? I got to be careful, right? How about this one? 1 and 4 with no equal at either end. I would just include 2 and 3. Because without the little equal thing below it, it doesn't want 1, it doesn't want 4, it just wants 2 and 3. So you add up those 2, 0.08 plus 0.32, you get 0.4. Less than or equal to 3. Would include 3, so it'd be 3, 2, and 1. Add those 3 up. So just by coincidence in this particular case, because there could have been other numbers here, like X could have been 0, negative. But anyway, less than or equal to 3 happens to be the exact same answer as that very first one we did, because it represents 1, 2, and 3. How about the next one? Greater than 3 means we do not include 3. So it's 4 and 5. 0.17 plus 0.22 is 0.39. And then I went ahead and did the extreme cases here. Greater than 5, nothing greater than 5, right? 0. Remember, and then the next one, less than 6. They're all less than 6, right? Add them all up, we get 1. Just reminding you that the answer can be 0 and it can be 1. That's 0 and 1 are possible. Let's take a look at this coin flip example. Flip a coin twice. I just kind of drew a tree here. You know, if I'm not going to do more than 2 coins, but if we did more than 2 coins, it helps if you draw a tree to follow to be able to list all the proper. Last week when we did the counting, we learned that means there'd be 4 outcomes. Could be 2. Remember, that was counting rule number 1. 2 times 2. If it was 3 coins, it'd be 2 times 2 times 2, which is 8. But I don't want to get all that messy. But anyway, I could do that distribution if you wanted to see it for 3 coins. But anyway, so here's the 4 outcomes for flipping coins. But the problem with this, to make it be a random variable, this is technically not a random variable. Random variable X has to be something numerical. So this problem needs to be rephrased in such a way that it becomes numerical. So let's see what we have here. We've got, let's phrase X. Let X be the random variable that counts the number of tails when you flip it twice, and you're just counting how many tails there are. So now we figure out a way to make this numerical. Now let's see how I got these 3 numbers right here. How did I get 0, 1, and 2? Well, if I'm flipping a coin twice and I'm counting how many tails there are, if it goes head-head, I got 0 tails, didn't I? 0. You flip it twice, you count the tails, you might have 1. You flip it twice, you count the number of tails, you get 2. So there's no other possible value of X. There's nothing else. If you flip that coin twice and you are counting the number of tails, you cannot get an answer that's anywhere outside of 0, 1, or 2. Let's look at the probabilities of these outcomes. Now, here's what I was talking about earlier with the dice when I mentioned, well, yeah, they have to add up to 1, but you can't just, you can't just make up, yeah, I could go 1/3, 1/3, 1/3, and that would make it add up to 1, but that's actually not correct for this problem. We have to think about this. Notice there are 4 outcomes. There's only 1 outcome that consists of 0 heads. It's the HH. 0 tails. 0 tails. This would have been the same answer, by the way, for if I would have said heads instead of tails. 0 tails, 1. So the probability you get 0 tails is 1 out of 4. Now, notice there are 2 ways to get exactly 1 tail. HT, TH. You have 2 ways to do that. So it's 2 out of 4. And I left it. I didn't reduce it on purpose. Of course, a lot of the stuff in my math lab is going to want decimal anyway. And then to get 2 tails, there's 1 way to do that. We get 1 out of 4. I left it like that because it makes it easy to add the fractions if you already have a common denominator. Okay, so each number is between 0 and 1, and they add up to be exactly 1. So let's say, for example, you put 1/4, 2/4, and 2/4, and you wonder why you're not getting the right answer. Well, that would add up to 5/4. So it violates this rule right here. It didn't add up to 1. So this adds up to 1, and it's correct. So there we go. Now here's one where if we take 10 ping pong balls, whatever you want to call them, and of course this needs to have something numerical. So let's say we take a Sharpie and we mark some numbers on them. We mark 2 of them with 1s, 3 of them with 2s, and 5 of them with 3s. And then we want to create the probability distribution. Over here, I just wrote the frequency distribution. To convert from frequency to probability, you just divide by the total, which is 10. There's 10 balls. But you don't have to, the part on the right, you don't have to really worry about that much. This is what we want right here. There's 10 balls in there. So the possible values of X, if you were pulling one out at random and just looking to see whether it was a 1, 2, or 3, you got 1, 2, 3. 2 of them are 1s, so you got a 2 out of 10. 3 of them are 2s, so we got 3 out of 10. And 5 of them are 3s, we got 5 out of 10. All my probabilities are good individually. Notice what they add up to. In other words, the idea on this, once again, is they add up to 1, they add up to 10 over 10. That doesn't guarantee I'm right, but not adding up to 10 over 10 means for sure it's wrong. Does that make sense? It would definitely be wrong if it didn't add up to that, but it's correct. It adds up to 10 over 10. Anyway, so there we go. Now let's talk about the mean of a discrete random variable. Now this one you could actually do pretty easily. You could just, average the add up the numbers and divide by 10. But we need this formula for other types of problems. So we want to, know this formula, even though for that one. Yeah, the mean also, represents the theoretical average if this experiment was repeated a large number of times, sort of like the law of large numbers that I talked about. If you did this over and over and over, your measured result should be close to the theoretical result. I'll mention that here again in just a second. Easy formula to do. All you're doing, don't let the symbols kind of mess. That's our mu is our population mean, and this is automatically considered to be a population because it's not a sample, because the x's are going to be the entire population of x's every time. So all you're doing is just taking each x and multiplying it by its own probability. X times p, x times p, x times p, and then you add those up. I'll show you how to do this in a calculator here in a little bit. You can do it in the TI. So for this one, you take 1 times 2 over 10, 2 times 3 over 10, plus 3 times 5 over 10, which is 2.3, which is it's just the average of the 10 numbers on the balls also. But what I was talking about is, how the law of large numbers kind of works with all this or whatever, So let's say if somebody did this, over and over and over 8 hours a day for their job for 40 years, or something or another, I'd get pretty old in a hurry. You'd get sick of 1s, 2s, and 3s pretty quick. But anyway, theoretically, and you recorded all their, results, the long-term average of all their measured results would actually, should be very, very, very close to that number, 2.3 right there. That's not important. So anyway. This book doesn't use the phrase monetary here, but I'm going to go ahead and leave it from a previous textbook. It's not a big deal whether I leave it or take it out. But it's the same formula, but now we're dealing with calculating this with monetary. What we're going to do in the homework, we'll do another one of these, where it's just a regular distribution. You'll see that again. But these monetary problems are kind of interesting. Let me just look ahead. I probably have something when I get to the variance and standard deviation. Yeah, okay, we got that coming back up again anyway. All right. You don't have to worry about this EMV notation or anything like that. I mean, I'm not going to ask on a test. I would probably just say find the expected value. I wouldn't necessarily use the word monetary there. But now this is what I was talking about earlier. This is our random variable x. It's net gain, loss, dollar amount. So you can absolutely have negatives here for your x. It's only your probability values that have to fit within a set of certain rules and guidelines. All right. Now, suppose, and obviously maybe this is based on, previous results over time, why these outcomes are the way they are. You don't have to worry about that. It's giving you the probabilities. So, you have a potential short-term business venture with a probability of 1 over 10 of profiting $12,000, a probability of 4 over 10 that we break even, and then a probability of 5 over 10 of losing $3,000. What is the expected monetary value of this venture? So let's look at it. It doesn't matter what order I put these in, and the distribution is just long as the correct probability goes with the correct x. It doesn't really matter what order. If you like to do, you want to go lowest to highest on the x's, no problem. Knock yourself out. But I kind of did it just sort of in the order I saw them in the problem. That's what I did. So we're going to profit $12,000, but we got a 1 out of 10 chance we're going to do that. Break even, of course, for everyone, all of you take accounting, that's just going to be 0, right? So, yeah, I don't think we have to be an accountant to know that. And you got a 4 out of 10 chance of breaking even. And then, so what you got to realize is when you read these problems, which generally isn't too difficult for business majors to understand this, of course, but when you see the word losing, that means it's a negative number. It doesn't, even though it doesn't have to show you the negative sign right there. Losing, this case, means negative. So it's negative 3,000, and that has a 5 out of 10 chance of happening. Now, the expected value or expected monetary value, however you want to call it, you just take each x times each p, 12,000 times 1 over 10 plus 0 times 4 over 10 plus negative 3,000 times 5 over 10 is negative 300. Now let's talk about what does that negative 300 actually mean? Because the negative 300 doesn't represent what's going to happen to you in any one outcome. There's only 3 things that are going to happen to you when you do this once. 12,000 profit, no profit, $3,000 loss. Here's what this means. This means in the long run, if you did this over and over and over and over and over lots of times, you try this over and over and over, you should lose about $3,000 per each time you do it if you did it a large number of times. That's not good from your perspective. That's pretty bad. That means, in theory, it doesn't mean this will happen, but obviously, yeah, because of course, you could do it one time, hit the 12,000 and then quit. That's why we're just saying, but we're just looking at this as the long time result. You should lose about 300 per each attempt. So if you do this 1,000 times, the expected loss, and once again, expected loss doesn't mean guaranteed this amount, but you should be down about $300,000. That doesn't sound too exciting to me. Negative expected values are bad news. Now, positive, also, there's also other factors to consider, even if it's positive, but and I'll mention that here in a minute. But you certainly don't want anything that's negative here, So, other than not as a business venture, that's what. But yeah, some things are going to be naturally a little bit negative, like casino gaming. But if you're only doing that just for a little bit of fun, and control your loss or whatever, then that's not a big deal. But we're talking strictly as a business venture. This is. Now here's another one. I got this. This is from like 3 books ago we used for this class. So I don't know what. Now it's kind of arbitrary definitions here. It's kind of that. And this is the way it was in that book too. No oil, some oil, much oil. All right, that's I know that's kind of vague, isn't it? But that's all right. We have all the numbers that we need to do this. So that's what really matters. So it's all laid out. Remember I told you earlier these probability distributions could be shown vertically or horizontally. Doesn't matter. So whatever this, negative 40,000, we whiff, we got a 25%, 0.25 probability that we miss and get no oil. A 70% chance that we get what's called some oil where we profit 10,000. And then we have a 5% chance that we profit 70,000 on the particular venture there. And then notice the probabilities. I'm mentioning that here, that they all, just showing you, they all add up to 1. So that's valid. Like I said, if they give you a problem out of a book, unless they made a mistake, it should definitely add up to 1. It would have to be a big time mistake. So let's calculate that expected value of this venture. So you take negative 40,000 times 0.25 plus 10,000 times 0.7 plus 70,000 times 0.05 is positive 500. Now, positive 500 certainly gives us hope that we would consider this, we would at least consider it. If it's negative, you don't even consider it. But if it's positive, you would kind of consider it. So this kind of represents a $500 profit per drill in the long run that you should average. But there are other factors to take in consideration. Bankroll is one of them. Like how much money, do you have to support this? Because you know, in the long run, it should average out to where you average about $500 per try. But these are the three outcomes. Let's say that, you know, you happen just by a weird probability fluke, it could happen. But let's say, you know, your first 5 ventures all miss. So you're out immediately $200,000 if they all happen to whiff there at the beginning. So that's what I mean by bankroll is, do you have enough money that you know, theoretically shouldn't run out? Now, like I said, the probability of 1/4, you're not going to, you know, you're probably not going to miss like 20 times in a row or something with that high of a probability. It's, you know, 1/4 times 1/4 times 1/4, that'd be really rare. But let's just say like 4 or 5 times would be, you know, reasonable. It could happen. And then, you know, did you have the money? What if you ran out of money before you started reaching some of these gains here, you know? So that's the only flaw. But at least from expected value standpoint, this has a reasonable possibility of doing. Let's take a, you know, you don't have to be a gambling expert here. Don't worry about this too much. You know, I'm just going to kind of look at this roulette wheel, and it's just a wheel with numbers, and you don't have to know all these odds or anything like that. But anyway, well, actually, you can figure out the probabilities if I'm just telling you it's a 38 spaces on a wheel. You can calculate probabilities equally spaced. 18 red, 18 black, 2 green. I've seen some with 3 green. That's not good. If it's got 3 greens, that's not good for the player. Well, anyway, let's look at your expected value in this game. Okay. Now we're going to bet $5 on black. We're going to walk up there and bet $5 on black right there. You see what happens. There's only 2 things. There's lots of ways you can bet on this game, and there's different payouts, and let's just, you know, they all have the same expected value, ironically. But anyway, 2 things are going to happen. You're either going to win $5 or you're going to lose $5. You're either going to be -5, you're going to be +5. If you win, they'll put a $5 chip next to your $5 chip. That doesn't mean you won $10. One means profit. So if you put a 5 there and they add a 5 to it, you technically won $5. So I'd have won $10. No, you really didn't. But there are some bets you can make that are 2 to 1 where you could, you know, win $10. You just don't on an even money color bet like that. You're not going to win 2 to 1. Yeah. Let's see. Well, here's an example I'll show you, like right here. If you bet on what's called this column right here, any of these 3 columns, those pay 2 to 1. So if you put a $5 chip there, then they're going to add 2 $5 chips if you hit it. So then you would have profited $10. But anyway, so 2 things can happen: -5, +5. -5. I'm saying it's 20 out of 38. How did I get 20? Okay, I'll tell you how I got 20. If we're betting black, everything that's not black, we lose. 18 reds, 2 greens, 20 losing numbers for us. So it's 20 out of 38. If we're betting on black, we have 18 winning numbers, 18 out of 38. Now, just so I notice I made this little note right here. Notice that. So let's say if you forgot the greens, for example, and you just put 18 over 38 and 18 over 38, you would check and see that they do not add up to 1. So you would have to, you know, see where you went wrong. Mine adds up to 1, so that's good. Let's do the expected value. It's real easy because there's only 2 outcomes here. That's what I like about this one. Not too many things to have to add up. So it's -5 times 20 over 38 plus +5 times 18 over 38. And that number ends up being in dollars, -0.263. So the theoretical average loss per play should be 26 cents. Now, you don't have to worry about that. I'll just tell you this calculation. I wouldn't ask this on a test or anything, but as a percentage of the $5 bet, you know, you take that divided by $5, that ends up being 5.26%. I just want to show you that's the theoretical take, you know, advantage for the casino. in theory, on all bets, they should profit 5.26% on this particular wager. Now, this is negative, so it's bad, as an investment. You don't ever want to become try to become a roulette player for business sakes or anything like that, because you're going to lose. However, don't let me discourage you from, if you're, having a fabulous Las Vegas vacation there and you just want to play roulette for a little while just for fun, they keep bringing the cocktails out to you. You're having a good time, maybe with friends and whatnot. Sure, it's okay. Just don't become a professional investor in roulette. In other words, don't treat it as a business venture. You treat it strictly as recreation and have a little fun with it. You might even win, because the idea is this means in the long run you're going to lose that. In other words, you bet over and over, you'll lose that much per play. But if you just play for a little while, you might come out ahead. So you just got to treat it as just strictly recreation, and not as a financial investment. So I want to mention that. So anyway, let's come down here. Now we're about to do variance. Let's do one more example real quick. All right, this one tried to trick us there a little bit, but they couldn't fool us. So you got a little, maybe a little, obviously this isn't a big, this might be like a car wash business, somebody sets up on their driveway or something. I don't know. You can tell by the numbers are pretty small, right? So whatever, you lose $30 on rainy days and make $120 on days when it does not rain. Certainly not a lot of business where you have to pay a lot of employees or anything. But anyway, if the probability that it rains is 0.15, calculate the probability. The car wash's expected profit or loss, but they told us it was profit, so we are expecting this to be a positive number. Now, notice they didn't tell us the probability of it not raining. Okay, well, we're going to use that complement idea that we learned back early on in probability, that first section. If there's only two outcomes here, if we know one of the probabilities, we can calculate that missing probability quite easily. So if the probability of rain is 0.15, the probability of not raining is 1 minus 0.15. So it's 0.85. So they tried to get sneaky there and not give us that number, but with only two numbers and we knew one of them, it's always just one minus the other. So they couldn't fool us. And once again, the word loses. Obviously, you got to give it a negative variable here, negative 30, and then there's your profit of 120. Easy calculation. Negative 30 times 0.15 plus 120 times 0.85. We expect to profit $97.50 a day. How about that? Not too bad. And let's move on to calculate the variance and standard deviation of a discrete random variable. This is going to be pretty easy in the calculator. I don't know who's that people that are actually listening, or how many anybody's going to be doing this manually or not. If nobody's doing it manually, we can go straight to the calculator. But obviously, I'm leaving this in the notes because someone watching this later might need to do it. But I guess so. But anyway, let's look at, there's two ways. This is the variance. That's the square there means the variance. There's two ways you can do it. Now for this formula, we have to know what we have to calculate the mean, which is right here. We've already seen that you have to get the mean before you can do it if you're using that formula. Now, there's two different formulas you can do this. Now, and then of course, I've said this a couple times before, and I kept saying that this is always going to be true the entire semester, that anytime that you have a variance formula, the standard deviation will automatically be the square root of that variance formula, automatically. So standard deviation will be square root of the variance. Now, let's come down here. Now I'll go through the mean real quick, and then I'll ask something else here. So, okay, so the mean, here's the distribution right here, and you can double check, but I'm pretty sure I've done this problem enough times where I know they add up to 1 already. So the mean is okay. The mean's easy enough. It's just XP, 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 XP. Add all those up and then get 8.4. All All right, so now I'm going to ask if it looks like there's 7 people here right now. So you get to decide what you're going to see here. I guess that's the advantage of being live, in the sense that, and I can help other people later, don't get me wrong, but are you 7, or are some of you going to be needing to use this formula, which is just a regular scientific calculator, or will you be using the TI? Because if you're just using the TI, I guess hang on before you answer. If you're just using the TI, I'll just show you that way only, and we don't have to, I'll leave this in the notes, but we don't have to go through the mechanics of going through all this if you're not going to need it. In other words, that's what I'm getting at. In other words, I'm not going to have to worry about showing you that. But don't feel bad. Like if you're the only one that needs to see it, that's okay. We'll show it. But I'm not trying to discourage anything. But is anyone that's listening not using the TI, like 83, 84, any of the TIs like that? Okay, I'm going to assume that no one's saying that. I'm going to assume that means all of you are going to be using it. I'll take that as a yes. Okay.
Yes.
Yeah, sounds like, yeah, so that's the, yeah, obviously, I just was waiting to see if anyone said no more than anything else. So, okay, but I have it illustrated how to do it with the formula. But if you don't, I'm telling you, you don't need this if you're using the calculator. But some people, I still need to teach it this way or show it this way for folks but heck, they can come to me later if they're not here now, So that's what I'm saying. Sometimes it does benefit for you to see the live show when it comes to stuff like this. So I can just skip this part. Now even though it's in the notes, me explaining it now, you don't need to worry about it. All right, it's going to be done just like this. And of course, I'm going to do this. Let me just explain this one, and then you're going to see a real live one in action here in a minute when I go to my math lab. I'll do a live one in action. Let me just explain this one right now. And then you'll see me do it here in a minute. So what I did is you stat edit like we've done before to put numbers in a list. We just have 2 columns here. You have one of them will be your X's, and your second column will be your probabilities, and make sure each one lines up. The order matters. The right probability has to go with the right X. Now, when we do this, we've used this 1-bar stats command before, right? Remember that for standard deviation, and we used it for quartile, same command. But now we're actually using this frequency list, whatever. We're actually, I'll show you how to put the L2 in there here in a minute. So now you got to tell it there's 2 columns. Now, one thing, let me mention this too, though, is be careful if you ever go back to, you're going back later to do something where you're only dealing with 1 column of numbers. You got to get rid of that L2 right there, just blank it out or whatever when you use it, because that's going to cause you problems if you're just dealing with 1 column there. You just have to get rid of that L2, which is easy enough to do. But anyway, and then you hit calculate, and then you see the mean, 8.4, which is what I got right here. But I'm actually going to show you this in real time here in just a second. I know you're excited, but you'll see it. But I figured why type that one in when I can just put the time better use to my math lab problem. So, hey, you can always go back and try this one too if you wanted to. I used the formula. I got, okay, here's the standard deviation. Now notice, because it knows that this one is not even the sample thing is not even, there's nothing there. So you don't have to even worry about which one. Because if you enter just a string of numbers, the calculator is going to give you both sample and population because it doesn't know. But it knows in the 2-column format that it's not a sample. So it's only giving you the standard deviation. 4.26. Now, remember that this is the same thing we had before when we were doing variances in the calculator. Recall what I taught you a while back is that the calculator does not give you the variance. But that's no problem. All you have to do, if it was asking for the variance, is, I don't know if you need all these decimals, but I mean, probably doesn't take you that long to type in all those numbers anyway, right? In this day and age, everybody's, except me, is probably pretty fast at texting. So you can probably do and type them all in, and then you hit the X squared key on the calculator. Well, actually, let me just do that real quick. I'll tell you what I'll do. Let me clear these combinations from last week. So 4.256759 I'll just stop there. 4.256, I already forgot my memory what it used to be. 759. I'll just do them all. You don't have to do them all really, but I'll just show you. 59331. And then you hit the x squared key. So in other words, to go from variance to standard deviation is square root. To go from standard deviation to variance is square, just like it was before. And there's that 18.12 number that I got by using the formula. Right there. But that's only a minor inconvenience, you know. I mean, the fact that it's getting you that standard deviation quickly and easily is tremendous, you know. So the extra effort to get that variance, I don't consider that to be too much trouble. So now for exam purposes, you probably wouldn't need all the, I'm just wondering, you know, because sometimes the My Math Lab, you know, it can be a little finicky or whatever. So it probably wouldn't hurt you to put those decimals in there and square it. And that way this answer will probably match up with what My Math Lab wants a lot better. But on a test, it's going to be close enough to where, I mean, there's no chance I have answers that say 18.12, 18.11, yeah, you know, 18.13. No chance. But My Math Lab is kind of rude. Okay, this is the same problem, just using the different formula. So if we're not using any formula, that's using this formula. The red one's the better formula if somebody was having to use the formula. But okay, so you can just completely ignore that. If we've already ignored one formula, you can ignore the other. And just showing you, see, I got the same answer. Everything worked out the same. Well, actually, though, I can put this one in the calculator. I've already done it, but, or I don't know. I could wait on this one too, I guess. You could actually try to do this one. But I'm going to do it in the calculator. I promised you that. So I just hate doing these same ones when I figure I can do it. I can put it to better use by doing it in My Math Lab. So once again, here's the X's, here's the P's. And then once again, you can just put them, you see, here's the X's, here's the P's, L1, L2. Everything spits out beautifully. Yeah, let's see. Let me wake up. I'll just start up the My Math Lab. Let's start a new window here, and let's wake up the My Math Lab and not do that. And you're going to be a whiz on that, no problem. Yeah, so the mean and standard deviation is going to be pretty easy. Yeah, the stuff we did a little earlier in the section, you know, with a greater than or equal to, figuring out what probabilities. Not that that's hard, but you've got to be just real careful with those. This is just putting the numbers in there. You don't have to even really put really much thought into it, which that's okay. All right. So this warms up. We'll knock this out, do a couple of these. We'll go on early break just to give us enough time for that, make sure that next section and see what happens, and rolling right along here. Finally getting the hang of this Zoom thing. It was kind of weird at first, but it still is kind of weird, but I'll probably be doing this one more semester this way. They wanted me to do a face-to-face one at the Northwest campus, which that's where I've used to teach Stat 3309. That's where my Lone Star job is, same campus. But I told them I didn't want to because I can't teach through, I can't talk through a mask. That would just be terrible. I don't know. And then the other problem I can see is, you know, I'm about to turn 60 here next year, so I'm kind of old. Hearing someone through a mask is going to be no. I can't do it. So I think I'll be doing this format one semester, and then hopefully by fall of 2021 I can teach without having to wear a mask and just kind of somewhat sense of normalcy here or whatever. But I'm happy with, I'm wearing my mask, go to the grocery store, go run errands, but I'm also not talking to people for 2.5 hours while wearing that mask. That's the thing, my face would get all hot and warm, and okay, enough of my problems here, but I was just entertaining you while this was warming up. So, all right. I don't want to get in a big long mask discussion unless you want to do it at the end of class or something. We can do that. But okay, these are just mechanical, calculating out the expected values for two different groups. I'm just looking through here. Just pick one. Nothing wrong with that one per se. This could be good. Let's see if this has everything I want here. Oh, this one's tremendous. Tremendous problem. I'll be honest with you, I haven't really researched this much to see what can be done with Excel, on this really. But, you see we're kind of starting leaning more toward calculator stuff, on this. But some stuff we do later, I might bring back Excel. Maybe we'll even look at it the second half. But this is pretty proficient with the calculator. And so I'm not, in other words, I'm not cheating you out of something I think that's much better. We could look into it, but I don't think this is that bad in the calculator. But maybe I should look at the Excel. All right, so I don't need to really put this on a scratch page because I'm not really going to be writing, any formulas down or anything. So let me, I just got to bring up the calculator. Well, 0 through 6, I can remember that pretty easily. The probabilities, I'll probably have to go back and forth. So we're going to edit. Here's a list. So I'm going to go up here and clear this list. I'm going to go up the top. And it's weird. You go up the top, you see the red clear I've got over there left? I hit clear. Nothing happens. But when I move the cursor down, it goes away. That's weird to me. Because I can see how someone can get frustrated. I'm hitting clear. Nothing happens. I think there's actually a clear list command in there somewhere buried in the calculator. But that's weird that you have to actually, then you move it and then it clears. Okay, this is simple enough here for me without having to. The next one though, my memory. I could probably do 3 of these at a time. 3, 1, 3, 7, 1, 2. 3, 1, 3, 7, 1, 2. Okay, I can do all these. 7, 6, 4, 3. All right, I think I got them right. Well, we'll know if it doesn't give us the happy check mark, right? So I always just go quit to get off the screen. I go second. Right next to it's the quit. I know I've said this before, but I just love how this calculator displayed this for students. It shows me the red thing, shows me the button I pushed in red. That's just tremendous. Stat, calc, 1 bar stats. Okay, so this one I'll be careful. Yeah, you see, normally when we're doing one variable, we just have that nothing there for frequency list. Now we need L2. To get L2 is an upper function. It's right above the number 2. So if I go second, it's a blue shift function. Second 2, that's bringing up L2. Second 2, not just the number 2. Don't forget the second. Now we've got it in there. But like I said, I was telling you earlier, if you needed it gone later, just go to that frequency list and you can hit the clear button, there, and that'll just clear it out. Enter. Let's see what we got. All right, I see a mean right there. 1.44. Let's give that a whirl. $1.44. How about an early excellent here? Give me an excellent. Nice work. I'll take it. Look at that. Standard deviation. So it's not even asking for variance, so we don't have to worry about that little deal, but just in case. There it is. How many decimals? 3. How about 1.564? I like that. Check. Look at us go. We are tremendous. I like this question too, because this goes back to what I was asking earlier in the notes there, where I had that, distribution. I asked all kinds of different less than or equal to, greater than or equal to. This is asking that, so that's good. All righty, so the probability that x is greater than or equal to 2. So obviously that equals very important. Actually, I think I will. Probably don't need to, but I'm sure you understand it okay. But maybe I will snip this out just to go ahead and get a scratch page going here. Probably don't need to do this, but it's not going to hurt anything. So let's do this. I can make it a little bit bigger too. Greater than or equal to 2. So we come up here. You agree? You think those probabilities then represent greater than or equal to 2? I think they do, don't they? I'll take that as a yes. So we'll start at 2 and we add down 2, 3, 4, 5, 6. So I'm not going to write that out, but just, we're doing this. We're adding those up. Oh, I'll try to be clever and do this in my head, and then you can laugh at me if I get it wrong. I don't mind. 19, 25. I mean, you use a calculator, obviously. Don't try to show off like me. 19, 25, 29, 32. I get 0.32. Okay, be sure to laugh if I get it wrong. And you could be thinking, told you should use a calculator. 0.32. Oh, got it right. Dang, sorry. No laugh. So was that all right? Just got to add up the correct probabilities that go with it. I want to see what's happening real quick in the chat thing here. Let me jump over for a second. Oh, okay. All right, that's all right. I say a lot of silly stuff, so no telling what that was about. I might have missed it earlier. So,
can you go calculator part?
Yeah.
Because I was able to put my list in, and I put my L1 and L2 in, like I physically wrote it in, but I don't know how to get to that part where you just were at right now.
Second quit.
Okay.
Did you do that?
Yeah. So I'm on a clear screen now.
Stat, calc, 1 bar stats.
Okay. And then when I get to 1 bar stat, I guess I might have an older calculator because it's not giving me the list how you have the list.
Okay. Yeah. I'm glad you. Okay, I'm with you. Okay, I'm with you.
It just says 1 bar stat.
Yeah. I'm with you. Hang on a second. I got you. I forgot about that. I'll write this down for you. I can't really simulate the 8. Yeah, I'm glad you mentioned that because I didn't remember to mention that next Monday. Yeah. What you do if it just shows 1 bar stats, you're going to have to manually put it because 1 bar stats, normally that's just fine whenever it's just one variable. So if you've done that before, you just would hit enter and that would be it because it's defaulted for L1 only. But to do both, when you have the 1 bar stats, you're going to have to, it's not that big of a deal, but you're going to have to go second, the number 1 to bring up L1, and then the comma, which I think the comma's right above it's not a shift, it's right above the 7, I think. Somewhere in there, the 7.
Oh, yeah, I see it.
Right above the 7, it's not a shift function.
Right above the 7. Mm-hmm.
Comma, and then go second 2 to get the L2. So L1, comma, L2. I'm glad you mentioned that because somebody else out there might be using the 83 also. I completely forgot about that. I'm glad you mentioned that.
And then I should just be able to hit enter from
Yeah,
there. Oh, okay. So let's see if this will.
yeah, yeah. I'm actually really glad you brought that up because
Oh, yeah, that did it.
so I completely forgot about that. So yeah, it's just it's still there. You just have to do a little extra. It's not that bad. Yeah. So hopefully maybe someone else has that 83, and you definitely probably helped with when I do this on Monday because actually I'll look like I'm clever and I'll be able to remember to say it before they ask. I'll look cool as I'll go, hey, if you have the 83 though, hang on, I'll show you what to do if you have the 83. Well, obviously somebody could be entering in the data if they have the 83, but I'll say wait and I'll show you how to do it. So, but no trouble if that's how you got. Yeah, you got a little tell at that or whatever. So, and it'll be that way every time. So there you go. So, beautiful. All right,
Thank
very
you.
good. That was important. We'll try another one of these and let's see before we go on break. Um, let me see. This one has. All right, let's do this one. This one has whole numbers, but I think you can enter it as whole numbers, or you can convert it to probabilities. I think it'll work just fine. Now, to answer part C, though, we're going to have to use whole numbers. But let me double check this and make sure that what I'm saying is correct here. I think it's going to work okay, even if you just use the whole numbers. In other words, to convert them to probabilities, in other words, you have to divide each number by the total. So it says 200. So you would divide each one. You can do that, but I think this will work without doing that, except for part C. All right, let's do this. So, okay, once again, I'm going to quit out of this. Stat, edit. Now, I'm not going to clear the list this time because I know that when I'm going to be typing in more numbers that were already there. So anytime I'm typing in more numbers that are there, I know I can just override them. When it's less, then you got to clear that list. Does that make sense? Because, yeah, if it's less, then you're messed up. So, oh, God, how many of these can I remember at a time here? If I could remember 4, that would be helpful. Ugh. 18, 31, 48, 41. 18. I already forgot. 31, 48, 41. 48, 41. Obviously, you'll be able to do this a lot faster because you'll be looking at your calculator at the same time you're looking at the numbers, unlike what I'm doing here. I guess I could kind of shrink the screen to figure out. Can I get these? Maybe, yeah, 20, 27, 20, 9, 5, 1. Okay. Let's see if this works. All right, so I'm going to quit out of this. All right. So we're going to go stat, calc, 1 bar stats. So you see that once you put that L2 in there, it sits there. But if you ever need to get rid of it, you just have to get rid of it. I guess for the person that's using the TI-83, though, it's better for you in that aspect is because you have to make the L2 appear or whatever. So if you're just doing regular 1 bar stats, it won't already be there. But here, if you're just kind of going back to single list data, you'll have to remember to get rid of that L2. Okay, this is doing this correctly. Oh, but you know what? It's actually, when it's not probabilities, it's doing it both. Well, it doesn't really matter. We're still using the population standard deviation. I'm going to show you something here in a second, too. But let's see. I think this should be okay. Let me make sure I get this right first. 2.775 for the mean. 3 decimal place. 2.775. Okay, so we could use whole numbers there. It's showing you the symbol too, the population standard deviation. I guess it was 3 decimals again. 1.756. Okay. Now, okay, here's a little trick I want to show you. Not necessary. I mean, I'll have to actually do this. Hopefully this trick will work. I can convert that L2, if I wanted to probabilities before I even did that thing. If I wanted to, if I go, okay, I haven't done this in a while, so hopefully I'll do this right. Since the 200 was the total, that's the key. I'm going to go second L2, and don't worry about this if this is not that important. Divided by 200, and then right over here to the left of the 1 is this thing STO, means store. Okay, so what that's doing, it means it's taking everything in L2 and dividing it by 200 and making a new L2, if I did this correctly. If I didn't, I'm bailing out. And now it's just showing you that way. So I'm going to go back to stat edit where we can look at the list. Just a way to convert them. But we got the first 2 right. Hey, look at that. But I'm going to do the stat. I'm going to do that command again and see what it does. Now I'm curious. That's what I thought. That's what I thought. Notice, not that it mattered. We still got it. But notice when I converted it to probabilities, it's the mean's still correct, but it doesn't even show the SX anymore. It only shows that population one. Fascinating. But that's okay. It worked without it. Now, what you're going to have to remember here, though, is if you don't do that, which is fine, totally fine, you go to, let's look at the question. So less than 2. So do you agree that less than 2 would just represent 1 and 0, right? We okay with that? I'll take that as a yes. So if I add together 18 and 31, I get 49. 49 is not the answer. It's 49 divided by the total of 200. So it's going to be 49 divided by 200. I'm going to go 49 divided by 200. Or, well, let me get this answer right first. Jump ahead of myself. 0.245. Let's make sure we get the green check mark there. 0.245. Got it. Okay, here's all I was going to show you is for that problem. Then we're going to go ahead and take a break on this now, I think, before we start the next half. Anyway, if I go back to after I did that store thing where I converted it to probabilities, you could then look at your list and get this answer by just adding those first 2 numbers. Because see that now they're probabilities. So if I added 0.09 to 0.155, I would get the 0.245. So you either add them as whole numbers and divide by the total, or you can do that little trick there where I did with the storage thing and I converted them to probabilities, and then just add the necessary probabilities together. I hope that didn't confuse you too badly with all of that there. But point is, you didn't have to do that store thing. You didn't have to do this part to get it right. That was the key. We were able to get it right without doing that. But I thought that was an interesting idea to do that. So, all right, let's take a look at this problem before we go on break here. This is the 5th one, 5.1.7. So you see you have 2 conditions here. And X's and Y's. And here are the probabilities. And this says anticipated return is $1,000 each stock. Okay, well, I don't think we have to worry about that too much. So let's enter these in the calculator. Now, so one thing you have to be careful about here, as I've discovered in the past, that you have to make sure that your X value, don't worry, that's a Y, that the values, the probabilities, in other words, have to be in the second column, and these values have to be in the first column. So let's make sure we do that, or we're going to run into an error. So I'm going to come up here. All right, I'm going to clear this out and do my stat, edit, and then I'm going to put the values in L1. Let me see what those, and I'll put the X ones in there. Let's see, negative 140, then 60, 150, 210. I'll try to remember all that, but I'll probably have to come back to it. Now negative, make sure you use this negative at the very bottom. Do not use the subtraction symbol. That will certainly give you an error. Use that little negative for negative numbers. I think it was 60, but if I'm wrong there, I'll change it. It was 60, and then 150 and 210. Enter 210. Now let's come over here and enter the probabilities. Point 1, point 2, point 4, point 3. Point 1, point 2, point 4, point 3. All right, so we can go do the one var stats and second, quit, stat, calc, one var stats, L1, L2, calculate. Now this is important. This will save you a little effort here. I've learned this from experience too. Because it's going to alternate. It's going to ask for the mean for X and then the mean for Y. Then it's going to come back and ask you for the standard deviation for X, then the standard deviation of Y. So go ahead and write down the standard deviation. I don't know how many decimal places it's going to want. I didn't look, but I'm just going to put 101.3361. I'll round it to 4 decimal places. It can't want more than that. And you see the mean is already 121, so we have that. But you'll be able to save that number when it asks for it. You don't have to retype the numbers in again. Save you a little time there. So I'm going to put in 121 and check answer. Well done. Now the expected return for Y, so we just have to, we keep the probabilities are the same. So we just replace column 1 and with those numbers. So we go stat, edit. I already forgot. Yeah, I had it right. Negative 80 and then 20. Negative 80. The probabilities are the same. And let's see the next two. 90 and 160. Be careful. Sometimes my eyes will drift over into that first column. So make sure we stay there. 90, 160. Enter. I'll go second, quit. Then I'll go stat, calc, one var stats again. The mean is 80. Now I don't need to write down this standard deviation because when it asks for it here in a second, I can just go right back to the calculator because it's for Y right now. Let's check it. It was that one that for X was important because now watch what it's going to ask here. it's asking the standard deviation for stock X, 2 decimal places. So that was the one where I had 1013361. So 2 decimal places means it's going to be 101.34. So that saved us from having to go back and type all the numbers back in again for X. Now it wants it for Y, and since we've just done Y, it's right there in the calculator. So 2 decimal places is 72.39. Anything that saves us a little effort is always appreciated. It would have been nicer, though, if they would have done standard expected return and standard deviation both for X and both for Y. That would have been polite of them. They would have done that instead of making us have to write that down. But by writing it down, saved us the trouble. Let's look here. See, expected value, you got expected return higher for X, but you also, with a higher standard deviation, means it's riskier, meaning more volatility. You have more chances of going up and down and losing more, more variation. So it's, look down here, it's going to be this answer. X should be chosen on the expected value, but it's also mentioning a larger standard deviation, which is the higher risk. So we're going to take that into consideration. Let's check that answer. Good job. And now we'll go on break. Does anyone happen to be logged into their Blackboard right now, or
Yes.
no? Yeah. Would you mind checking to see under the course content, do I have a folder called charts and tables or something like that, something named like that? Because I need to.
You do. Yes.
Okay. Yeah. This one I'm going to be using today. Thank you. This should probably be in there then. So I'll double check. So, I mean, it's okay to refer to it during the lecture, but obviously the second this lecture is over, actually I'd rather be there in case you wanted to bring it up, but there should be one called Binomial Probability Table or something named like that, so, but yeah, I got to get that in there for sure. If it's not in there, the latest at the time class is over, but of course you're going to see me bring it up and work with it, but okay. Thank you for that. Appreciate it. Let me see what's going on. All right. Okay. Now, the binomial distribution is a specific type of discrete probability distribution. There are several. We don't have time in a class like this to study over them, but there's one called a Poisson, a geometric, a hypergeometric, and just they are discrete distributions that have specific rules applied to them. Of course, they all have the same rule, where all the probabilities have to add up to 1, but there's other conditions. And the binomial is the one that's, most likely to be used, in the real world. You'd more likely see that than anything else. So maybe the Poisson, but this one, so that's why it's the one that's more logical to study. So that's why we're going to study that one. So let's look at some of the rules here. All right, it consists of n identical trials, meaning it has a stopping point, which actually there aren't, because the reason that's important because the geometric one doesn't have an actual stopping point. But anyway, maybe like flipping a coin 10 times, or rolling a dice 20 times. It has a specific total number of trials, and each time you do the thing, that's considered a trial. Now, this is where it gets a little interesting here, is that when we have each trial results in 2 possible outcomes. One is called a success, and the other one's called failure. That doesn't necessarily mean, good or bad in the sense of, good versus evil. It just means success is the thing you're trying to measure, and then failure is not that, not happening. So like, for example, if you're doing a problem where you're measuring the probability of defective calculators, well, if you're saying probability of 3 defective calculators out of a batch of however many, strange as it sounds, but that's considered the success because that's what you're measuring. It doesn't mean it's a good thing. All right. Success or failure, and the same thing with probabilities. When we look at the probabilities, we only consider 2 probabilities. An example of, well, let me talk about number 3, and then I'll use an example of that. Well, we're gonna see that coming up here anyway too. But now the probability of success on any one given trial, I kind of highlighted that and made that large, is lowercase p, and the probability for failure is q, which q is 1 minus p. And that goes back to the idea that we've learned about complements. In other words, if you've got 2 outcomes and you know the probability of one of them, the other one has to be 1 minus that one. Kind of like that car wash problem we did in the last section. Yeah, so only 2 outcomes, it's 1 minus the other. All right. Now this, some books do this, and I find this really annoying. So I'm not changing my entire notes for this, but it's important that I mention this to you here, show you in writing and verbally. The probability of success, this particular book uses the pi symbol, which I don't like that because pi is an actual number instead of lowercase p. Maybe I don't know why they do that, why some books do that. Maybe they do it so they don't confuse lower p with capital P. Capital P means the probability. Well, it won't be that hard to make a distinction. You'll see that as we scroll down, the difference between lower p and capital P. So the My Math Lab is probably going to use the pi, but the pi means this same lowercase p. They're the same thing. And you'll see me, we're going to do My Math Lab homework, so you'll see this in action. So yeah, but I'm going to be using, I didn't want to change all my notes to, who knows, down the road, the next book they go back to, it might go back to P again, so it's been P, it's in P for, several books now, I don't know, but anyway. And the last condition is the trials are independent. One trial would have nothing to do with the next trial. So, things that are independent, like rolling die, flipping coins. Now, some things would have to be, replacement would have to come into play, like this. Cards, drawing cards is not binomial unless you replace the card and have the full deck in there every time. Because the probability of success on one trial needs to be, for this rule, for this binomial, it's got to be the same every time. And we've learned from all that stuff we've been doing in the last couple of sections last week with obviously, not replacing the card, that affects all the probabilities. So in other words, but they would not be independent, because if it was a card, you pull it out, you don't put it back in, whatever card came out is going to affect the next probability. All right. So we're going to roll a single die 30 times. We're going to identify N, P, and Q, and they're telling us we're considering a 3 or 4 together. It's considered a success. So the idea here on success and failure means that we either care about getting a 3 or 4 or not getting a 3 or 4. In other words, if it's not a 3 or 4, we don't care whether it's a 1, 2, 5, or 6. We don't care. They all bunch together. Those 4 numbers go together as just falling in the failure category, not a 3 or 4. So we don't look at all 6 things individually. It's either, so it's failure or not failure. So the single die is rolled 30 times. That's going to be your N. Now here, the lowercase p, which I'll just say this, which this book is calling pi, is the probability of success on one trial. You have to ignore the 30 to answer this question. You have to ignore the some people want to include that 30 in there. You just think of this P means what would happen on just one trial, one time. Well, 3 or 4, there's 2 ways you get 30. 3 and 4 combined, right? 1, 3, 1, 4 makes that 2 out of 6. I went ahead and reduced it, but that's okay. And then Q, I don't have to count up all those other numbers, 1, 2, 5, and 6. I know if this one is 2 out of 6, the other one's going to be 4 out of 6, because it's always, Q is always calculated as 1 minus P. And then I reduced them to 1/3 and 2/3, which it's not mathematically important by any means, but it is a true statement. Okay. So we are interested in finding the probability of X successes in N trials. Now here's the formula. But guess what? This is going to be in the calculator. So you don't have to use this formula. So this formula, now here's what we're talking about. This is the capital P, means the probability of X number of successes. And then that lower P is the one I was telling you is known as pi. So I don't know if that's why they use pi, but I don't like pi because, you know, pi is an important number in mathematics. I don't like it being used as a variable, in other words. I wouldn't use 2 as a variable either, you know, so I don't know. But anyway, so the probability, now this first part of this formula is that, I'm just telling you, that's that CNX or NCX or however you want to write it. That's that formula we saw last week. I believe that was the last one of those counting rules, counting rule number 5, how to find the combinations, because the order doesn't matter. So if you're trying to measure X successes and N trials, you're not, the order they occur doesn't matter. You're just trying to figure out, you know, they could, you know, wherever they appear. So there's no order. And then you have the probability of success raised to the X power, and then the probability of failure raised to the N minus X power. So if you're just kind of using a scientific calculator, you would need to use this particular formula. And I think some of these, I wrote them out just so people that are using a scientific calculator can, you know, see how it's done. They can always ask me later. But we've already established that for the folks that are here tonight, we can just use the formula. But let me just kind of show you this, and then for this one, and then show you how the formula sets up. Just never hurts to learn. This is using the older calculator, but all right, so they're telling us that N equals 10, X equals 2, P equals 1/3. That's kind of ironic. This actually matches our dice problem up there, even though it doesn't say that, you know, this same P, 1/3. Well, the N's not the same, but I mean, the N is 10 instead of 30, but that's okay. X is 2. So we could actually use that example. To relate that to that dice problem, this would be the same as saying if you roll that dice 10 times, what's the probability you get exactly 2, either 3 or 4? Remember, 3 or 4 both work. So what's the probability you get, you know, that happens twice out of 10 times? All right. So using the formula, you'd use that combination formula. Last, you know, there I did it with the factorials, and here I did it with the NCR formula. And then the P is 1/3, and that formula says it's raised to the X. The X is 2, and then the 8 comes from the 10 minus 2. So there, right there, 10 minus 2, N minus X. So these two exponents always add up to be whatever N is. So if that's 2, so that kind of makes sense. If you're doing it 10 times, you're saying, and you're measuring 2 successes, you would have 2 successes and 8 failures. But the combination part here just takes care of all the possible orders they can appear in. You know, they could, because it can appear in more than one order. So this takes care of that part of the formula. So using the formula, we get 0.19 rounded, 0.1951. So thinking this as a percentage, then you're saying there's about a 19.5% chance we would get a 3 or 4 twice in 10 rolls. About a 20% chance we'll get exactly 2 of them. All right, so ready to put this in the calculator? Now I'll talk a little about this binom CDF. You know, you never really have to use that one, and it's got to be careful with it. Now we'll make sure I address the TI 83 issue now. I'll remember, since that has already come up. So, because the newer calculators are going to display it a little bit differently. So I'm going to come over here and I'm going to quit out of this. Just clear that. I'm going to go second vars. It's bringing up that DISTR. So second vars. You see the vars is lit up in red. Second vars brings up the DISTR, and you got to scroll down a ways to get to it. In the older TI-83, it might be 0 instead of A here. That doesn't matter. But you're looking for the one that says binom. I think they added another function in there as they upgraded, not one that we're even going to be using, but they added something in there. So yours, it might be 0. But just make sure it says binom PDF, not the one below it that says CDF. We want binom PDF. All right, if you're using the 83, hang on here, man. I'll explain to you what's going to happen. So if you're using the newer one, it's going to bring it up where it looks like this. It's going to prompt you for that everything. 10. And then the P is 1/3. The X is 2. Then we go paste. Now, if you use the binom PDF, it should just bring up binom PDF. It may give you the left parentheses. If you're the one person that's using that, does it give the left parentheses when it does that? If you're trying it or not, or in other words, it might just open it up with, I can't remember if it gives you the left parentheses to start the thing out with or whatever, and then oh well, maybe that person's not here anymore or whatever. But
no, I'm here.
I'm using a TI-83. Where did you go to get that bino?
Second vars.
Okay.
Distribution. It brings up. You scroll down just like I was doing. Got to watch me whenever I do it. Watch me when I do it.
Yeah,
I'll be doing it again or whatever. But
yeah, I missed it. So, but I'll continue to watch and then I'll follow you on the next one and let you know.
Yeah.
Yeah, you just watch. Yeah, but I wanted to prompt you for how it's going to look when it comes out on the 83. Is all I was trying to show you. But if you want to just wait for the next one, that's fine too. Then so yeah, that'll work just as well. Yeah.
Okay.
All right, then I'll wait.
Oh, but it did pop up for me. I'm sorry, and it does pull up with the parentheses.
Oh, just the left parentheses, correct?
Yes, that's correct.
Okay, thank you. Then what that means is you just have to enter these numbers like they show right here by putting the commas between them. So you'll go 10, comma, 1/3, comma, 2, close parentheses. So you just have to manually enter them in there. It doesn't prompt you with that other screen, and you'll end up with this same thing. You just have to type the numbers in like that. So, and there it is. Yeah, you just have to type them in there. It's important though that you put it in NPX order. I'll go wait till I go back to notes. You'll see. There's the answer, 0.19. You're going to see this done again. So obviously, that was not your only chance. Yeah, see how I have that written right there in the notes? N. So if you're typing them in there, you go N. It'll start the left parentheses, N, comma, P, comma, X, close parentheses, and then that'll do it. All right, we're going to try this again. Well, this is actually true for any discrete distribution, but binomials, though, the x's are on the binomials. The x's can only go from 0 to n based on that. That's what it would be every time. There'd be no weird. There's no negatives on the x's here, because if you do something a certain number of times, the number of successes you can get can be any number from 0 to whatever. If you flip a coin 5 times and you're measuring tails of successes, you're either going to get 0 tails, 1, 2, 3, 4, or 5. It's either going to be 0 up to whatever the maximum is. But that's just mentioning it has to add up to 1, because that's the general rule that we've already seen for a discrete distribution. All right, now we'll do this one in the calculator. Roll a die 20 times, and we're just saying rolling a 5 by itself is considered a success. So all we care about is whether it's a 5 or not a 5. If it's not a 5, we don't care what it is. It's just not 5. Yeah, so it's either 5 or not 5. All right. And let's see what we got here. So n will be 20. P is 1 over 6. So keep in mind, you don't, the 20 is obviously part of the equation. It's very important, but you don't let that affect. In other words, if that could be 20 or 200 or 2,000, this P means the probability of rolling a 5 on any one trial would always be 1 over 6. So don't use the n value to influence what you think P is. You just think of P, or pi as they do in this book, as what would happen on one time. And of course, Q is always 1 minus P. You don't have to even, it's just 1 minus P. So if you got a 1/6 chance of success, you have a 5/6 chance of failure. So what's the probability that we roll exactly 3 5s and 20 rolls? Here it is using the formula. I have it set up there. If you want to look at that, and then I'll just go ahead and just skip over it though. But you know, if you want to ask about it sometime, that's fine. But since it doesn't appear we're doing it here, so here's in the calculator. So yeah, there it is using kind of the old calculator way. So okay, watch this carefully. Second, watch how it lights up over there. Bars, look where it lights up right there at bars. That distribution. You got to scroll down. Like I said, it might be 0 on the 83 if I remember correctly, but it's A on this calculator.
You're right. It's 0.
Yeah, because they added something new in there. So just make sure it says Binom PDF, not CDF. So second bars, you got to scroll down and get to it. Actually, you probably could just hit the number 0, and that will probably take you to it or whatever. I think you could try that. Or yeah, doing the letter A is too confusing. It's better just to scroll. Okay, so once again, yours not, the 83 is not going to see this, but though you're going to enter the numbers in there. So it was 20 trials for this one. So you'll go 20, comma. So what comes from this result is exactly what you type in the calculator. I believe it was 3 was the X, I think. We'll check. And then paste. And then all it's doing, it's pasting what you would get if you just typed in the numbers. 20, 16, 3. So it's not that, so using that, there's nothing wrong with it. The 83 works just fine. You just have to know it goes NPX order. And here we go. And okay, there it is, 0.2379. So you basically got about a 23.8% chance you'll get exactly 3 5s and 20 rolls. Isn't that exciting?
Very.
Now, let's say we're going to take a multiple choice exam with 25 questions and 4 choices for each question. That's very important for a multiple choice exam to be binomial using the idea we're just guessing. In other words, no knowledge whatsoever. In other words, you could just randomly fill out a scan. You don't even need to see the test because that's the whole idea of this. You're just randomly picking letters because you don't even need to see the questions because you're not using any knowledge or anything. But for this to be binomial, it's very important that you have the same number of choices for each question. Because a lot of my exams would not be binomial because you might have 3 choices for one, 4 for another, because it's got to be the same probability of success for every question to be binomial. Now, of course, true false doesn't have to tell you how many choices there are, right? Because it's obvious there's 2. But multiple choice, though, this could have been 5 choices. So multiple choice doesn't have an assumed number here. It's got to tell you. That could have been 5. So telling you 4. So that tells you purely by, so we know their n is 25. So by pure random guessing on any one question, we would have a 1 out of 4 chance of guessing that question correct. Therefore, we would have a 3 out of 4 chance of not getting it right. So let's suppose we're going to guess. And we want to know what's the probability of guessing 20 correct out of 25. Let's just say we need to make an 80%. That's 80%, right? 20 divided by 25. We need to make an 80%, and we're just going to try to do it by pure guessing. Shouldn't be too hard, right? Probably not, huh? So here's the formula set up with the combination part right here, and then 1 over 4 to the 20th, 3 over 4 to the 25 minus 20. And look at that number. In fact, this comes out in scientific. I don't think on, now I don't know what's going to happen in the homework, but there's no way I'll put one in the exam that comes out in scientific, that's really that weird, but this is a good problem. So we have 25 trials. 1 out of 4 is the probability. 20 successes. So times 10 to the negative 8, what that means mathematically, that scientific notation, it just means you take the decimal and you follow the bouncing ball and you move it 8 times to the left, and every gap you leave, there'd be a 0. So basically, what happens is there would be 7 zeros in front of that 1 after you move it over 8 places. 7 zeros. And that's what I moved. That's there. I wrote it. So I wrote it out, and there's what it is. Yeah, actually, I think I'll avoid that for testing purposes. That's extremely, extremely low. So guess what? You're basically not going to pull that off. It's not 0, not absolutely, but yeah, good luck with that. Because you're actually getting into, and if I feel like I have a little more time, but I probably don't want to get too much off track here so we can get through with all this, but maybe if I have some time later, I'll show you. But you're now getting into the realm of winning the lottery, that kind of probability. You're in that area. You're close to that, which is kind of weird because if I change that to 5 choices per question, winning the Powerball would be, you'd have a better chance than you would of doing this for sure with 5 questions. Now, if I had more time, I'd go through the math. I ought to write up a little something and just sort of attach it at the end of the notes if people wanted to look at it. But it's hard to do it, in class because of time. But anyway, but that's hard for people to comprehend, but I can show it numerically because it just seems like you could pull this off better than you could winning the lottery, doesn't it? Just because the lottery, sort of mentally just seems incomprehensible. This is actually incomprehensible. It just doesn't seem like it. Mathematically, it really is. 20 out of 25 guessing multiple choice? No, you're not going to do it. But anyway, okay. Yeah, maybe one day I'll do that. I'll just add a little blurb at the end of the notes and just show that for anybody who's just curious to look at it without wasting class time. Hey, maybe if I do it, sometimes I'll think about it here in the near future. I'll let everybody know, hey, I added something at the end of the notes if you just want to look at it. Now, let's talk about, we're going to look at adding, now we're going to start looking at less than, greater than or equal to, less than or equal to, which means we have to add several, binomial probabilities together. And which means I'm going to introduce that binomial table, that chart I was just showing you. Now, like this one, now suppose if you were doing this and this was a test, I won't go through all the numbers here just to save time. But let's say if you were trying, I got to make an 80 on this test by guessing. Well, obviously you would be interested in guessing, instead of not just 20, but 20 or more, right? Obviously anything more than that is good too. That would be helpful. But, I've done this before, and I think I took it out of the notes, but like I said, it wasn't that important. I wouldn't have asked it on a test for these weird numbers. But anyway, let me just tell you that 20 or more doesn't really add much value to this answer right here, because if you think about it, if this 20 is so unlikely, what do you think 21, 22, all the way to 25, they're going to get even smaller. So when you add them together, it's not really increasing this by much. But that would be saying if you got at least 20 right. It's just the numbers are so weird for that one. So let's do that. Now the binomial tables, the problem is they don't work for all situations because it's really impossible to have an infinite set of tables to do this in. But I'm going to show you how I like to do this for testing purposes. Hopefully the homework will go along with this. But if not, I'll sort of explain to you how I do this for testing purposes. Now let me come down here and show you this. So just kind of show you, you know, some of the wording, and we'll be dealing with this again. You know, we've talked a little bit about this, but is means equal, is not equal. At least means greater than or equal to. Fewer than, less than. Strictly means, it's kind of blurry. It's hard to see that. At most means less than or equal to. And more than, above, is just strictly greater than. Now let me show you how this table works, and I'll sort of, what, you know, in other words, you might be wondering, why aren't we just using this table all the time? Well, I'm going to explain that. But we're going to use it for certain situations. But it's just kind of, you know, we'll see the whole table here in a minute. Look at how you read this. So you need to find, you know, if you're using this table, you need to find what your n is. And I think my tables go 2 through 20. But obviously, theoretically, n can be larger than that. And I just have some these are the different possible probabilities. So they don't include you can't include every probability. It's impossible, because the p can be anywhere from 0 to 1. So theoretically, it could be, well, here's an example. Roll, you know, probability of single number on a dice. 1 over 6. 1 over 6 is a repeating decimal point, 1666666. Yeah, so you really can't represent every number on here. So this is just a possible set of probabilities. Now, notice that whatever your n is, and we've talked about this before, x can take on anything from 0 to whatever n is. So if n is 2, x can be 0, 1, 2. If n is 3, x can be 0, 1, 2, 3. So forth, so on. You know, that's going to be, the x's can go from 0, and then the maximum value is whatever n is. All right, let me scroll down here. And we'll use the tables for this one, because this one actually fits the table. Actually, the one I was just doing fits the table too. I'll show you that one. But that would not be very, very mathematically useful for that question I did earlier. And I'll show you why in a second here, but this one will be. Suppose we have 20 questions with a probability, you know, 1/4, so 4 choices. Find the probability of guessing no more than 4 correctly using the binomial table. So what's the probability you get 4 or less right strictly by guessing? And we're going to use the table here. Now, this is the important part. Well, I mean, reading the table is important, but once you learn how to do that, you'll have that skilled master. But this is the important part right here in the light blue, that you have to realize that no more than 4 means less than or equal to 4. That's important. And what that represents is 0, 1, 2, 3, 4. So if we were just using the regular binomial formula, or even in the calculator with a binom PDF, here I'm mentioning that we'd have to do 4 more calculations. You would have to do 0, 1, 2, 3, 4, and then add them up. So it's a little time consuming. It wouldn't be too bad, you know, if you do the binom PDF, because you could just go the first one, and then you don't have to even get the individual answers. In other words, you can go binom PDF and then just go plus binom PDF plus, and wait to the end and hit enter and add them all up. But okay, we're going to use the table, which will be a lot faster here. So let me bring up the big table for now. Oh, yeah, I forgot about that. My math lab's going to get quiet on me. That's going to be a little hard to see here. That's okay. You should have a, we'll go down here to 20. And we know n is 20. And you see, you'll be looking at the actual top. Yeah, you got it. The P's are on the top of each page. So you see the P's aren't directly above the 20s, but they're above the 19. So you have to pick what column you want to be in. So I'll just highlight that. So actually, we can fit everything on this one. We can see it. That's good. But sometimes we can't. Because sometimes I'll tell you that if it doesn't fit, I'll go, okay, it's the 5th column. But you see, it's the 5th column, right? It's the 0.25. 1 over 4 is 0.25. And I want 0 right here. 0, 1, 2, 3, 4. And I have it nicely snipped out in the notes. I'll go back. 0, 1, 2, 3, 4. Might be hard to see that cursor right there, but it's that block of 5 numbers right there. It'll be much more clear here in the notes, and there it is. So there's the 0.25. Here's the 20, less than or equal to 4. You just highlight those 4 numbers and add them up and get the answer in one step. Pretty slick, huh? Now, you can get away with not, because people sometimes will ask me about that Binom CDF. Boy, you know, if you want to try to use it, just, you got to proceed with caution on this. Frankly, you never have to use it, never. So you can just pretend like I never said this to, but there's always somebody, you know, people that will be curious and want to use it. But Binom CDF means cumulative. And we know what cumulative means. We learned that earlier in the course. Less than or equal to, right? It's less than or equal to that number. So since this was a less than or equal to problem, since it was less than or equal to 4, I could use the one right below the Binom PDF, which is a CDF, and I can enter 20, 0.25, and 4, and it got that same answer right here, 4148. But you have to be careful because Binom PDF for 4 would not be the right answer. Now look what Binom PDF 4 yields here, 0.1897. And look what that is up here in these numbers. PDF is just the individual number for 4, the 1897. The CDF is adding all of those up. But the PDF is just giving you the one number. So, you know, to do the PDF, you would do it for 4, 3, 2, 1, 0, or 0, 1, 2, 3, 4, whatever order. It's giving you each of these. That's where these numbers are coming from. Except I think I used an Excel command to generate this spreadsheet. We can look at the Excel. I forgot what it was, but I'm sure we can figure it out if we want to. If we need to, we can take a look at the Excel. But I don't know if it's worth the trouble or not. It's just so easy to do it right there in the calculator. But anyway, yeah, I was using a binomial command to generate these values. And, but so the CDF, I did just be very careful and realize that it only means, you know, less than or equal to. Anyway, so let's try another one of these kind of problems, and let's see. Got a binomial distribution with n equals 16 and p equals 0.6. Find the probability of more than 10 successes. Okay. We have to be very, very, very careful here that we realize that more than 10 is not the same as 10 or more. 10 or more would include 10. More than 10 does not. More than 10, because these are always whole number integer values, so it would jump up to 11. So I can go back to the full chart real quick here just a second to show you, but I just snipped out the important part. So 16 is up here. And then the 0.6. Okay, what column is it? I'll count 4, 5, 6, 7, 8, 9, 10, 11. It's the 12th column over. But like I said, if you just kind of look at these pages, the whole page, you'll be able to, if you're able to print them out, that might not be a bad idea for testing purposes, just so you can do it quicker, you know, or whatever. Because if you do it the way I'm doing it here, it's kind of a pain. Because if you go down the bottom there. But anyway, so it's the 12th, what did I say, the 12th column, 10th column? I already forgot. 5, 12th column. So, but I can already see it's this column right here. I've already just visually, it's that column right there. So you would start at 11. I believe that's 11 right over here. Yeah. And then add all the way down through the 16. Now, the CDF does not work for this one because the CDF is for less than or equal to. So that's what I'm saying. CDF only applies certain situations. So it might be best for a lot of people just to completely ignore it, not even use it. You know, if I thought it was critical and you really needed to use it, I would tell you that. But it's probably easier just to use this table. But like I say, this table is convenient. It's because, you know, we don't have, that way we don't have to do 6 individual calculations. We only have to do, you know, we just can look at these and add up that 4 block of numbers and come up with it just like that. So that's, now here's what I'm telling you, for exam purposes, so that means but the table doesn't do everything. What I do is I'm always going to have one problem, maybe two problems, where you're going to have to use the binom PDF because the probability might be some number like 0.37 or something that's not on the table. Now, some of the homework problems, I think the probability is on the table. So if it's on the table, you can use the table, but I'll make sure as I'm putting together, I'm working on this exam review and putting this exam review together, I'll make sure there's some where it's not on the table so you'd be mentally prepared. But this means you have to use binom PDF. However, any test question for binomial that I'm going to put that involves adding two or more probabilities, it's going to be something off the chart. Now, whether you use the chart, that's up to you. You could still do them as individual binom PDFs and add them together. That's your choice. But I'm just saying you'll be able to get the number off the chart. So if it's adding two or more, you can expect it to be will be off the chart. But just one probability, you'll have to use the binom PDF. So I'll make sure it's not on the chart. Just so, obviously I want you to use either the formula, but it sounds like everybody here is just using the binom PDF, which is, that's perfectly fine. So I want to kind of clarify that a bit, but obviously in the homework, if it's off the chart, you can use it. So this does not totally replace the binom PDF. All right, let's take a look at this one. 25% increase military spending. So if you select a freshman at random, your probability of choosing one that selects it of success is 0.25. So if 6 are selected, find the probability that fewer than 4. So once again, fewer than 4, the same thing as less than 4, so we don't include 4. So less than 4 means 0, 1, 2, 3. And I won't go to the other table, just to save time, I'll go right here. And I just labeled it for you, that's the 0.25 column. And then the 0.25 column. And let's see. And then there's 0, 1, 2, 3 for the X's. There are those 4 numbers. Add them up. It's 9624. Oh, okay. Here's something on the CDF. Okay, okay. You can use it, but you got to pay attention to this. If you realize that less than 4 is the same thing as less than or equal to 3. See, less than 4 means less than or equal to 3. You could use the CDF and do it that way, because it just drops down to the net. So see, the 0, 1, 2, 3 means less than or equal to 3. So the binom CDF at 3 was the same answer as adding up those 4 right there. But like I said, I'm not trying to confuse you, but people will tend to ask me. I mean, I would have had to have taken it completely out of the notes and just said ignore it, but I already had it in there, so I thought I would at least explain it since it was there. But I'm also explaining that you can choose to forget about it. All righty, mean, variance, and standard deviation of a binomial random variable. Okay, the bad news, this cannot be done in the calculator. But the good news is it's so simple. Well, I mean, I'm not talking about multiplying numbers together. I mean, there's no, list, stat, edit, all that stuff. But the good news, the super good news is it's a really, really easy formula for this. So it's not any trouble. So to get the mean, all you have to do is take the value of n times the value of p. That is literally it. So not bad. For the variance, you just take n times p times q. Remember, once again, q is always defined as 1 minus p. And guess what? If you hadn't heard me say this enough times, here it comes again. Standard deviation is always the square root of the variance. So if this is your variance formula, NPQ, you can bet everything you own, the standard deviation formula will be the square root of that. So I know it sounds like, same, okay, keep saying that over and over and over, but you see it's true every time. The standard deviation, no matter what the variance formula, will be the square root of that formula. All righty. 20 question multiple choice exam, 4 questions. What is the mean number of successes? Find the variance and standard deviation. Okay. The mean, we know the 1/4. We've already established that earlier because there's 4 choices. So you have a 1 in 4 chance of getting that correct. So it's literally just 20 times 1/4, which equals 5. So what is that? What's that telling us in the scheme of things here? This means on average, but in other words, when you guess like this, no one's expecting you to not get any of them right. But in theory, you should get about 5 out of 20 right. Because if you're guessing, if you have a 1 out of 4 chance on any one question, that means about 1 out of every 4 questions you should get right. Does that make sense? So you should get about 5 right. But obviously the idea but the guessing is great. If I get 5 right, though, that's kind of a failing grade, isn't it? So that doesn't really help me much. A couple times years ago, I guess I quit doing this because it kind of time purposes or whatever reason, I don't know. But well, obviously we're not going to do that now because we're not meeting face to face. But I just kind of gave the students a bunch of Scantrons I had sitting around and just told them to randomly fill out 20 answers, and then I just randomly made up a 20 question key. There wasn't even a test involved, and then I could break or whatever, or bring it back to the next class period, and then just see how many were where people were getting right, and so you would see like 3 or 5 or 6 or 7. I think 11 might have been the record high I think I got for somebody getting it right, but the most, so. Just to see what the result, but that just means if you took samples of a lot more than that, like thousands and thousands and thousands of people, and you average them all up, you would expect it to be that average to be around 5, because that kind of makes sense. Now these numbers, you're not really trying to speculate what they're going to be, you just calculate them. Variance, NPQ, 20 times 1/4, and Q would be 3/4. I just wrote it out like that, so 20 times 1/4 times 3/4, 3.75. And then the standard deviation will just be the square root of that. I'm not going to put that in a calculator for now. We'll wait till we do a math. There's no program to it, but I'm sure you can use the square root key in your calculator. But we'll do a problem where you have to get the answer right. Here's one where I just made up an n. I made up a p. If n is 40, p is 0.15. Q would be 1 minus that, right? So it'd be 0.85. Same thing. Mean would be n times p. 40 times 0.15 is 6. The variance would be 40 times 0.15 times 0.85, which would be 5.1. And then the standard deviation will be the square root of that, 2.26. And there you go, square root. So there you go. Okay. All right. Okay, I'll kind of skip through this one real quick. But anyway, one dot. So we're saying we just had to pick one of them. One dot. 2. I could have picked 1, 2, 3, 4, 5, or 6. So you just have all you have to realize here, as long as you realize the probability of any single dot thing is 1/6. I could have used 1, 2, 3, 4, or 5. So that's easy enough. We'll do this in the My Math Lab. So just kind of. All right, so now we're going back to a binomial question. This was kind of an interesting question just from a thought process here. The wording with that word not in there. We enjoy thinking, don't we? Okay. Oh, that's a rhetorical question. Try not to make your brain hurt too much there. I like this. Good business sort of question here. Worried about whether our business is going to get shut down or not. All right, probability we produce a defective item is 0.05. That seems kind of high. I think first thing I'd be doing, if it was even I thought it was that high, we'd be examining quality control a little bit, wouldn't we? But anyway, just for this process, maybe I'll redo these numbers for future generations and and lower that number a little bit. We take it, so somebody's going to come in and just, somebody from corporate maybe is going to come in and check us out, our plant, and you're the plant manager. You're walking around, you're the supervisor. You got your clipboard and your hard hat and your mug of coffee. You're walking around supervising. So You take 15 items. If they come in there and they find more than 2 are defective, more than 2, they're going to shut down for maintenance to see, okay, what's going on here? Why is this happening? Now the wording here though is asking find the probability that we will not be shut down. And a lot of times these questions will say, okay, you can assume it's binomial, but sometimes they'll put that in there just to, yeah. So it's telling you can use the tables, but you don't have to use the tables. But so here's the key. If more than 2 means shut down, less than or equal to 2 is not shut down, 2 or less. So if they come up with 2, 1, or 0, we're not shut down, 3 or more. So we're calculating not shut down. That's going to be a little bit easier too. So fewer numbers to deal with. So that's the only thing about this problem is just the trickiness of the wording. The math's not that bad. So n is 15.05, less than or equal to 2. Okay, I wrote this out with the formulas, which many of you don't need. I don't know what this first one I did it this way, but I'm glad I did just because it's there. Now you could do the CDF on this one because it's a less than or equal to. I could do the CDF, but I just did 3 binom PDFs just to show you that. But heck, you can just get it right off the table and have it done. Now it's a little bit off because of the rounding. You wonder why this doesn't quite match to that last decimal place. That's because the numbers that are on that chart, are rounded to that 4th decimal place, which since they are rounded, obviously this one doesn't round to the 4th decimal place. So that's why it might be just a smidge off there or whatever. Hopefully the homework would only ask it to 3 decimal places, then we would be in good shape. But anyway, I would just do it with the chart and just go 0, 1, 2, n is 15, p is 0.05, add them up and be done. But, you can use the CDF if you feel comfortable with that. But I certainly wouldn't do it to 3 PDFs unless you want to. I mean, if you want to do it that way, it just takes longer. Anyway, answer is 0.9639. So that means we've got a 96.4% chance we will not be shut down. Let me come over here to the chat thing and see if there's anything I need to do. The X the X has to be given, because you can't make the calculation without the X. So there's no way it has to ask you to, it has to say, okay, we want the probability for this particular X value. Yeah, because then it would just be unknown information, So that would be no good. So if it wants the probability. Now, of course, it could give you a situation and just the question could say, okay, identify what's the N and the P. Then, okay, if that's all it's asking for, then, there wouldn't need to be an X. But if it's calculating the probability, there absolutely better be an X. So we've got a pretty strong probability here that we won't be shut down. So that's good. Obviously, a higher percentage, the better. Okay, here's the mean, variance, and standard deviation. All right, that's easy enough. I'll just kind of skip over that one for time purposes because we're going to go to the homework and look at one. Now here's one. Okay, pass driving test, first attempt, 0.65. 11 people are selected at random. What's the probability among these 11 that passing the test is between 2 and 4 conclusive? Conclusive, not yet. Well, inclusive, not conclusive, inclusive, meaning between 2 and 4. I don't think, honestly, if I would use this per se on a test, or if I did this on a test, I would probably use the symbols, but inclusive does mean both 2 and 4. So this one's just 2, 3, and 4. So long as we realize it's 2, 3, and 4, it's not that difficult. I did the binom PDF. So you go to 11. There's obviously 0.65 is not the first column next to this. It's not right next to it, but obviously for visual purposes, I'll put it right next to it. So I would just add up the 2, 3, and the 4. And I got 0.499, which seems to match that green check mark right there. I'm kind of going to jump through these real quick so we can go to the My Math Lab. Here's another one. 63% favored police substation. So that's 0.63 is your probability. 14 are chosen. What's the probability? Exactly 10. Yeah, so here's an example I was talking about where the tables are irrelevant. You just have to do the binom PDF. But you're not adding stuff together either. Exactly 10 means X is only 10. So this is exactly what I'm talking about, what could represent a test question where the tables don't apply. But anything I ask you where it's adding probabilities, I promise you it's going to come from the table. So I just did a binom PDF, 14.63 and 10. Got 0.1845, rounded to 3 decimal places, 0.185. All right, so let's just do a fresh problem here, even though I didn't enter those in there. So, all righty, to the homework. Let me pop through here. There's 5 problems. Let me just kind of see what looks exciting. All right, so we've talked about this. There's that little pi they're using. Pi means lower p. That's just mean and standard deviation. I'm going to skip over that. Maybe mean and standard deviation will be included in another problem where we're doing probabilities. I can come back to this, but let me look at this one. I think the mean and standard deviation is actually pretty easy, so maybe I won't even do that at all. Maybe I'll just focus on this, but we'll see how it goes. Let's look at this one. I was hoping they would have some with a couple of probability questions and then, the mean and standard deviation all in the same problem. Or heck, I could just do one of those mean and standard deviations. Oh, this one's a thing of beauty right here. This does have both. I like it. Ooh, tricky. Well, don't mean to scare you here. A little trickier than what I would ask on a test. I'm going to snip this one over so I can bring it to the note. Well, I was just looking at one of the questions, not the entire problem. It's not bad, but don't be scared because I groan there. But we're gonna have to outthink this problem a little bit. Show you. I don't know why. Okay, well, I could have stayed in the other page for that one. Anyway, that's all right. Main thing I want is the part C. I want to make sure I copy that over. All right, so you see the probability online orders fraudulence 0.04. So there's your P, which they call pi here. 25 orders are replaced. Assume that online retail orders that fraudulent is binomial. Mean and standard deviation. Okay, mean is just n times p. So I told you there's no fancy formula here. N was 15, I think. I already forgot. I know this is 0.04. Let me double check. Let's see if that was the right numbers. Nope, 25. Dang it. I thought that felt wrong. It's 25 times 0.04. Oh, that's just going to be 1. 1. Let's put 1 in there. Got it. Standard deviation. It's the square root of NPQ. Obviously, that's in the notes there. I won't go back to it, but I'm just, you can go back and see that. So I'm going to go ahead and I'll clear this. N is 25. P is 0.404. Q. Now you can do this as 1 minus, or you can figure out the number. It's going to be 0.96, but just to be on the safe side, if you just want to do it this way, this is fine. Just do it that way. That's your 1 minus P, which is 0.96. If you want to, in other words, you can figure that out first. It's up to you. I think this is just good as anything in my book. All right, I'm going to see the number of decimals at once. I always forget to look at that before I do the problem. 3. 3, I'm going to go 0.978. Hi, what? What do you mean that's not right? Oh, ha! I got dyslexic here or something. I'm not trying to make fun of a disability here or whatever. I looked at it as if it was 9779, which would be 978. This number rounds to 980. Holy cow. That dang, I start getting blind here at the end of the evening. It's 980. I just rounded wrong. Holy cow. That was freaking me out. I'm going, I know I did. Okay. I know I did that right. Ha! So let's try 980. Yay! Oh, goodness gracious. Sorry about that. What is the, actually, I don't need to cut and paste this one. I think we can do it. I can explain it verbally just fine. 0 orders turn out to be fraudulent. So that's your X. X equals 0. So like, see, the person was asking about the, we didn't need X for mean and standard deviation. You don't need an X. There's no, X is not required. But as soon as you start calculating probabilities, there better be an X. Or X is plural, if you're adding them up. So we're just going to do I'm just going to do a binom PDF since we've already decided that everybody's that's listening today here is going to do it that way. So it goes NPX and 25, happens to be the same number, coincidence, 0.04, and then the X is 0. And then you'll see on the next screen, for those using 83, you'll see that's the order you manually enter the numbers in. All right. Does it want 3 again? Because you got to be careful. You can't assume anything. 4, see? That's what I'm telling you. Yeah, it changes. Let's make sure I think I can get this one. I'm going to go 3604, rounded to 4 decimal places. Excellent. That 1 will be fraudulent. I think you can do, let's just try this. If you use this second, and it should work on, if it works, it'll work on the 84 or the 83. I don't think I have to redo this. I think if I just go second, enter. Yeah, there we go. Back up, type right over it. How about that? Isn't that slick? Look at that. Enter. Boom. Brings back the last command, 3754. Look at that. Excellent. We are too cool. All righty. Okay, this one I'm going to copy over because we're going to have to outsmart it here. Because we're not going to be able to use the table for this one because 0.04 is not one of the ones that's on the table. Like I said, for testing purposes, I'm guaranteeing you, as I've said several times, that this kind of question would be on the table. And who knows? When you do it, maybe that probability of that P value will be a number that's on the table. But it's probably good that this isn't, so we can all right. So we just write down symbolically what's going on. Okay. Without the table, and if we were doing this directly the way it's asked right here, we would have to do the probability that x equals 2, but we're gonna outsmart it. Plus 3 plus dot 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 all the way to 25. That's 23 calculations. I mean, even though we're using Binom PDF, that's still a pain in the butt, even with that. We don't want to have to add up 23 of these, do we? I don't want to. Not when I can show you a better way to do it. But involves, understanding that, okay. Now, I mentioned this earlier. I haven't actually used it until now. But the sum of all of the possible x values, now I'm going to use, now I'm going to go like this. I'm not going to worry about putting 3 in there. I need to make a little bit of room here. Now, this was in the notes. I didn't spend that much time talking about it, but I did verbally mention it. But now we actually need to use it. I mentioned that because this has to follow a discrete distribution and the x's go anywhere from 0 to 25, that those probabilities have to add up to exactly 1. Okay, that's just kind of the rule of the land there, basically. All right, now, let's give these variable names. Simple letters. I don't want to use X, though. I'll call it B. How about that? B is what we are trying to find out based on what I wrote there in blue above it. Agreed? We're trying to find B. And what if I call this A? So, hang on here. Not doing too serious an algebra here, but so with that writing, do you agree then that A plus B equals 1? Okay, I'll take that as we're okay with that idea. Then just, that's what I'm trying not to go too fast here. So then using just basic algebra, would you agree that B equals 1 minus A? All right. So what's my point of all this? All we have to do is just calculate what A represents, which is these two probabilities added together, and then go 1 minus that. And that gives me the same answer as if I would have done all of those added together. So I guess now we better make sure I'm right here, right? So you see how I kind of shortened that up a lot, didn't I? In other words, into a much simpler calculation. So, and because that's less than or equal to 1, you can use the cumulative, but you can use Binom PDF. I'll just use Binom PDF twice just to show you. So what am I about? Okay, it's 25 and 0.04, right? I should know these numbers by heart now. Oh, you know what? Actually, yeah, they're using, okay, they're using the results well, I say coincidence. I think they did it on purpose. The 0 and the 1, we can just use those. So I'll use the rounded answers. That's probably what they have in my math. But yeah, just logically. So if I take those two numbers, add them together and go 1 minus that, that's going to be the answer. So it looks like that's how they designed the problem. But I'm going to go ahead and I'm going to go 1 minus, then I want to put these in parentheses. I could just go 1 minus minus. That would also work. 0.3604. I would highly recommend doing, especially because this part of the problem, to do this homework problem, as quickly as possible, possibly even either right now or just as soon as we're finished, while this idea is fresh on your mind. You come back to it a few days later and go, what the heck? So I think it's going to be 2642. Fantastic. So that was pretty crazy way we came about that, wasn't it?
Yeah.
Because it would have been not pleasant the other way.
Can you go to your previous screen right quick? It was so.
The scratch screen?
Yes, sir.
Yeah, you got it. Here I go. I just want to get that answer entered first. And yeah. So the
Okay.
answer's entered in there. So
And then.
see, the A represented those two numbers I added together that we actually had gotten, and which I could have come up with those if they didn't already have them there, but we already had answered them for those other two questions. So I just used the ones we'd already done.
Okay.
Because it just happened to be the right ones we needed, which what I'm thinking is they intentionally set it up that way is my thinking. So it was just those two numbers, one minus those two added together.
Okay.
Trick. I know that's why I wanted to carefully, because I wouldn't have expected you to figure that out, but, and that way that's good, because that's, if not, you would have tried to do it the other way and probably would have got frustrated really quickly here. So, I think we're about out of time, but let me just kind of, obviously people are free to leave whenever they want. I thought I'd at least try to do another homework problem real quick, if that's okay. I'll skip those first two with the mean and standard deviation. Those are pretty easy, I think. Obviously that's when I said I kind of made that noise or whatever when I saw this. I saw that last question on this problem before we did it, and I knew that was going to be. So maybe we can, let me see if this is kind of the same thing. Yeah, this is, excuse me. Yeah, this one's similar to that one, so we might as well knock that one out real quick if you want to. And sorry, I'm going to go a couple minutes late here. My apologies, but I think it's good that we see this. But like I said, I don't check in the class attendance or anything like that. So if I go a couple of minutes over, you weren't forced to stay. That's always important to remember, right? You have free will. So this is more for your benefit. We'll do this one and we'll call it a night. And let's see. So obviously the numbers changed here. So blah, 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 LED light bulbs, 6% are defective. Suppose a random sample is 10% of LED light bulbs. What's the probability that none are defective? Okay, so you see the 0.06 is the probability. So once again, that's not going to be on the chart. So we'll use the Binom PDF. So let me clear all this out, and I'll do second distribution, same thing, Binom PDF. Okay, I've already forgotten the numbers again. So it's 10 and 0.06, and then there was none. None means, of course, selecting 0. I already have the 0 there, so we can leave it. 10, 0.06. The 0 is already there. So 5386. Nice work. Exactly 1. Starting to look like that last problem, but it's going to be a little bit different though. Three, 4, 3, 8. Good job. Good job. Good boy. Good girl. I feel like a little puppy or something, you know. Pat me on the head, hands me a little milk bone treat there. That's a good boy. No, I just can't. I'm sorry. I'll quit acting stupid here and focus on business. 2 or fewer. 2 or fewer, not fewer than 2. 2 or fewer. That's going to be less than or equal to 2. 0, 1, and 2. Are we okay with that? 0, 1, and 2?
Yes.
Now, we can do it 2 ways. We've already done 0 and 1, correct? We can then do it for 2 and then add it to those 2 numbers. However, if you feel comfortable enough to do the cumulative, how are people feeling on that cumulative? Because I already mentioned that you can completely ignore it if you want to, but if you like it, you know, you can use it. I don't know, maybe I should. Let me just do this real quick. I'll tell you what I'll do. Let me do the Binom PDF for 2. Let me check what's in that chat here in just a second. I'll come over to that chat. Be right. Let's see. I'll put the 2. And then we can add those 3 up, 0, 1, and 2. Or if you think you're developing some sort of comfort level on that cumulative, because it's a less than or equal to, remember the cumulative only is a selective use kind of thing here, 10.06. So when you put the X value in the cumulative, it's, see, Binom PDF is only calculating that one X value, just 2. Cumulative means it's calculating less than or equal to 2 and adding them together. So what I'm saying is this answer we just got right here would be those top 3 added together. So I'm just going to go ahead and use it if that's okay with you. Since I did show you the PDF for 2 and you would add it to those other 2 that we already had. And let's try this, 9812. Look at that, we got it. Just check the chat real quick, make sure. Oh, laughing at me. Some people just say I'm not quite right in the head there, but that's okay. Let's see. All right, 3 or more. Okay, let me come back to my scratch page. It's going to be, now you'll see, I think you'll be ready for it when you do it as a homework problem, but it kind of follows this. But if you sort of shift it over a little bit, so this time, actually, okay, I'll rewrite it. Let me just forget the X part. I'll just put P of 0. Just know it means X equals 0. 1, 2. I'm just trying to speed things up here a little bit. And this was 10, right? Yeah. So 3 or more, you could add them up, but you know, actually we can use the answer we just got. They did this way on purpose. If I do the whole A, B thing again, this answer right here, we just got. We already have it. We had that last answer was that A part right there. So if we do just another B equals 1 minus A, and we already have A this time. Last time we had to actually calculate something there, didn't we? I think for that one to the other one. But this one is already set up to where it was done, I think. Yeah, see, part C was 2 or fewer. So if I just go 1 minus that answer, so it's 1 minus 0.9812. But like I said, these are going to be on the binomial charts, these adding them up. So you don't have to even worry about any of this mess. You'll be able to add the numbers up off the chart. But we just have to do it for the homework. 0.188. Ta-da! How about that? So I'm going to call it an official lecture here, but I'm not necessarily running off. So we consider, as far as upcoming plans, I'll just tell you real quick is that now the next section is kind of lengthy, but I'm going to do it the way I do it every semester. So I'm going to keep it's a lot of content. So even though it's just one section, 6.2, I break it up into 3 components for the notes. I call it part 1, part 2, part 3. So that's how you'll see it listed and when I update the notes. And between that and one more section, it's going to take a couple weeks to get through the material. So we're probably, if you're curious, exam wise, it's probably a good 3 weeks. I figured probably last one was the end of September. You can probably think end of October for this one. So no panic yet. I'm working on the review. Got to keep the notes updated. So we still got some time here. So there's no panic on the test. It's going to be like in the next week or 2. We got good 3 weeks for sure. They're probably going to work to where they're going to be like the end of September, end of October, probably like the end of November, something like that, is my guess. That's probably the pattern and we'll follow. That kind of makes sense and everything will be covered. So, but that just in case you were worried about that. So, anything else you need some help with? And we've got a hurricane coming here or whatever, but it may not even come here though. I don't know. I feel sorry for people in Louisiana. Every time a hurricane seems to aim at us, it makes a right turn and goes right into Louisiana, doesn't it? At least these latest ones have. Poor people. Anyway, let's just see. Okay, chat here. But like I say, if there's anything you want to ask about, this is your time now. So,
I have a couple questions, Professor, if nobody else does.
Absolutely. Are they about hurricanes? I don't know much about hurricanes other than that. So you probably know more than I do. That's all I know is they seem to kind of curve away from us here lately. They don't always do that, right? But all right. So you tell me about hurricanes. Anyway, okay. So, oh yeah, we'll take turns. You ask your questions and yeah, we'll let someone in if they want in. Don't worry. So if anybody's waiting, you can put something in the chat and I'll get to it, but you're first, so you can be first here. So what do we got?
I just had a quick question on the part C on that problem.
Part C?
So,
okay.
So
right.
And then, so mine's actually, on my problem, it said the probability that 4 or fewer. So I think you said I would have to find, I guess, the third, of course, and the 4th.
Oh yeah, so yeah, yours has a little. If you do it just by individual PDFs, you would have to do a little bit more there. Let's see. I'm just thinking about something here. How did I get?
So you went up to 2 because it's 2 or few. I think 2 or less, right? So
am I on the right problem? Is it this one with
no,
the LED
yeah.
bulbs or the other one I did?
It's that one
Okay.
because then you also use the C something.
Yeah, I use that the CDF one or whatever. So
yeah, and so I guess my numbers didn't come out. Okay, I guess I didn't follow you after that.
All right. Did you want to do? Listen, I'm asking if you want to because you don't have to. Did you want to use the CDF if you're comfortable with that, or?
I don't know how. I missed how you used it. So when I have to make sure that I keep up with the numbers not interrupted in my calculator.
Okay.
Is that right, or?
Yeah. So if it's 4 or fewer, then you would just use the CDF for using the number 4.
Oh, okay.
Yeah, because it'll take it and it'll add it up as. But like for this problem, it doesn't matter. Like I say, that people have to be careful with that CDF because let's say if a question said fewer than 4, you would have done CDF at 3 because it would have stopped at 3. But this means, it's going all the way up to 4 or less. So you would just do the CDF. So you got to make sure, your probability percentage might be different than mine too, obviously. So, I'll do it in the calculator if you tell me what your numbers are.
Mine's are.
So what's your failure rate?
10.
Wait, that's 10.
Wait.
What's the percentage?
I'm sorry, 8%.
8. Okay. Thank you. But it's the sample size is still 10 or whatever.
Yes, sir.
Okay. So it might be keeping that fixed and just changing the percentage, I'm just curious what it's doing. So, all right. Well, okay. Let's see. Yeah, we can do it for yours then. That's fine. So we come down here. So if you feel comfortable with that CDF, but like I said, on an exam, you'd be able to use that chart. You wouldn't have to worry about it. So 10, and I got to change this to 0.08.
Mm-hmm.
And then you said 4 or fewer, right?
Oh, it says 4 or fewer. Yes.
Right. So you see what I'm doing there now? You see that?
Yeah.
See, that's what you should have in yours.
Mm-hmm.
And you should get enter and then hit enter. And hopefully that will be your value.
I guess I'm doing something wrong because I keep getting error. I typed exactly what you have, 10, comma, 0.0. Yeah, I typed the same thing, but for whatever reason, it's not keeps giving me an error message.
I was going to say, I was going to say, you are putting commas there and not periods, right?
Oh, let me double check.
Period in front of the 08. I'm just looking when it says error. I'm just looking for syntax is the first thing. I mean, but it could be something numerical that you put in there wrong.
Let's see, 10, comma, 0.08, comma, 4. Yeah, it's.
And you're putting the last parenthesis as well?
Yeah.
Yes. Uh-huh. I don't.
I without seeing what you have, I don't. I can't analyze it without seeing it.
Yeah, I don't know if it was because it's a T83. Does that matter, a TI-83?
No.
So you're trying to get C, right?
Yes.
Number 4.
Yes.
So I added up all the ones like he said originally. Remember, Professor, you said.
Yes.
So I added all 3 up, kind of like how you did, and then I was able to get the correct answer. But I didn't have to do all the numbers like he did. I just did the 4. I just went 4 decimal places.
Okay.
And added those up.
Yeah, that's fine.
Yeah, that's how I did the first problem that we did together, and then but with this one I wanted to try the CDF, but I guess it didn't. I don't know what I'm doing.
I don't know why you're getting an error. Now, what I was going to say is if you were using PDF, you still wouldn't get an error. You would just get the wrong number. It would be the wrong answer. But I don't know without seeing your screen, I can't tell how you would have. If you have exactly what I have, I don't understand how there's an error.
Yeah.
I mean, I got to visually see it somehow.
Yeah.
Because that's what when it says error, I think it means, I don't know, if some number's there that doesn't belong, or like if your probability had 0.8 without the decimal in front of it, just the number 8, that would probably give a decimal, or commas instead of, it shouldn't generate an error, in other words, without something being entered incorrectly. If you put it in there just like I have, I don't see how it would produce an error.
I should try mine because I didn't try it.
Yeah, do you mind entering that CDF? Someone else enter it and see what make sure what's going on.
So I'm going to do the binomial CDF. And then it's 10. And then mine's actually 9%. So 0.09.
Oh, okay. Yeah. Okay. That's fine. I just want to make sure you don't get an error or whatever, just to make sure you enter the numbers in there. And I wish I could see.
And then you're putting a 4 at the end?
Yeah.
Yes.
Yours might be different though.
Yeah.
Hers said 4 or fewer. The one I did when I brought it up was 2 or fewer, I think.
Oh, for C, mine says 2 or fewer.
Then you used 2. I just did 4 because hers said 4. Yeah.
No,
but
it's
then if
popping up. So
if you put
for
4,
C,
you're not going to get your right answer, but it should not yield an error. That's what's confusing me, is I don't know what's causing it to be an error.
Yeah, so I did it, and it did not give me the error. It gave me the answer, the same answer that I added up.
Oh, okay. It must be me typing something wrong.
Oh yeah, I wish this is the one time I really wish was a face-to-face class, just so you could walk up and show it to me. That would be dang, because I
I
like
know.
that.
I wonder why your C. So question C is asking in the question. It says, "What is the probability that 4 or fewer?" It doesn't say 2.
No, it says 4, and then D says 5 or more. So
Yeah,
then I would
yeah.
do,
Wow,
how
that's
would I
One,
weird.
do 5 or more? Do
one
I
minus.
just,
It's set up to do the one minus. It'll be one minus whatever answer you get for here. Yeah, it's set up exactly to be the same calculation as what I did. It's set up to be one minus this answer. But this error thing you're getting is concerning. I don't can't figure that out. But the last part, if you do get this right, figured out, it'll be one minus whatever you get here.
the 0.9999?
If it's 4, 19994, so you'd go 1 minus 0.99999. Type that in real slowly again. I mean, just go, let's see, try it again and see if, let's go real
Yeah, I
slow
was
and
gonna
see.
say, in your numbers on the top are 10 LED lights, and then you have 8%, I guess.
Hers was, she said,
Manufacturing.
was 8%.
Yeah.
Hmm. Yeah, I wonder
I don't know
why.
why this is displaying in scientific notation, why it's not showing. Let me check the mode
I
here.
got I got that one too.
Uh, I guess you can go in here into the mode and make it be a certain number of decimals. That's stupid that it shows it that way or whatever. I mean, I have it in normal mode here. Maybe all of these should just show us. I'll just go 6 decimal places. I don't see what it does. Because at least I'll do the same thing. But it's 0.0006.
It's what?
That's not going to show it. I don't know why. 3 zeros and then a 6. I don't know why I can't get this out of scientific notation mode for this number. I don't understand. That's weird. I don't know if those other ones. I don't know how to fix that.
Professor, I'm so sorry. I did, instead of a comma, I was using a decimal, and that's why it wasn't going
I
Oh,
knew it.
through.
It had to be some sort of typo. I'm not
I
giving you
didn't.
a time, but the only way it's an error is if something is just, but like I said, you can get the wrong numerical answer, obviously, if you don't put the right numbers in there, but an error had to be syntax. So, okay, wonderful.
Yes,
Well, you
I
looked
did it
at it.
slow.
Yeah. So was it right after the 10 you said you had the decimal? And you probably had a
Yes.
comma. You could have one decimal and have the comma right the second time. But if it's
Yeah.
wrong anytime, it's going to blow up. So, okay, that makes me feel better. It had to be syntax. So, yeah, okay, now you're good.
Yeah. Okay. So I'll
Does your
wait for.
calculator also show that 6e to the -4? That is weird.
Yeah, I did also show that 6e -4.
I don't understand because I always thought it would just show. Um, I don't remember working with calculators before to where it did that for that. What's going to happen is it's going to show scientific notation in like that one I did with the guessing the number or whatever on the tip when it's too large, or too many zeros in front of it. Then it's going to go into scientific notation. But there's enough room on the screen to show 3. There's enough for 3 decimals, 3 zeros. There's enough room. So I don't know why it's doing that. That really bugs me. And I don't know how to necessarily fix that either. I don't know if changing those other modes would do it. Let's see. I thought you just always leave it in floating mode. I thought floating mode then would just do whatever it wanted to, and it would choose decimal setting. I don't know what math print and classic means. I don't know the difference between those two. I have no idea what that means. I'll try it again and see what happens. I'm sure that didn't do anything. No, I give up. That's bizarre.
And then I don't know, Gustavo probably had another question or symbol. If not,
Oh
I
yeah,
do
let me
have
see
one
what's going
more.
on. Yeah, you chime. Let me check the chat real quick and just see if anybody's waiting. If not, they can. All right, thank you. Good evening. End of October. Yeah, right. The end of October. That'll be about probably expected around then, somewhere in the Halloween area, somewhere around there. Not that you don't have to take the test on Halloween, but probably that weekend. Maybe it's good luck. Dress up as a giant pumpkin. You might do better on the test. I don't know.